Let's start with the most famous story in physics. You've heard it 1,000 times. Isaac Newton, sitting under an apple tree. An apple falls and hits him on the head. Suddenly, inspiration strikes. He discovers gravity. Beautiful story, simple, memorable, perfect for textbooks. Completely false. Newton never claimed an apple hit his head. The story was invented decades after his death, romanticized and simplified for popular consumption. What actually happened is far less dramatic but infinitely more interesting. Newton did observe an apple falling. He said so himself in his later years. But it didn't bonk him on the head. He was thinking, contemplating why objects fall the way they do. He saw an apple drop from a tree in his family's garden at Woolsthorpe Manor in Lincolnshire, England. This was around 1666, during the plague years, when Cambridge University was closed and Newton had retreated to the countryside. The observation itself wasn't remarkable. Apples fall, everyone knows that. But Newton asked a question that changed everything. Why does the apple fall straight down? Why always toward Earth's center? And here's the leap. If gravity pulls the apple down from the tree branch, does that same force extend higher, to the treetop, to the clouds, to the moon? That was the insight. Not that gravity exists. People knew things fell. The insight was that the same force making the apple fall also keeps the moon orbiting Earth, that the heavens and Earth operate under the same rules. Before Newton, most scholars believed celestial objects and earthly objects followed completely different laws. The heavens were perfect, eternal, governed by divine geometry. Earth was imperfect, temporary, chaotic. Newton unified them. One set of laws, one force, universal gravitation. He didn't figure this out instantly. It took him roughly 20 years to work through the mathematics and publish his results in the Principia in 1687. 20 years of calculation, geometric proofs, and wrestling with concepts that had never been formalized. The apple was just the beginning of a very long journey. But the myth persists because it's simple. It fits our desire for eureka moments. The truth is messier. Science rarely works through sudden flashes of insight. More often, it's slow, methodical work, building on observations and mathematics over years or decades. So forget the apple hitting Newton's head. Remember instead that Newton asked why. Why does the apple fall? Why does the moon orbit? And in answering those questions, he gave us the first mathematical description of gravity that actually worked. This is going to sound wrong at first. You've spent your entire life being told that gravity is a force, one of the four fundamental forces of nature. It pulls objects together, keeps you on the ground, makes planets orbit stars. Simple, intuitive, wrong. Well, not exactly wrong. Incomplete. Newton's description of gravity as a force works brilliantly for most purposes. It predicted planetary motions with incredible accuracy for over 200 years, but it doesn't explain what gravity actually is. Newton himself admitted this. He could describe how gravity behaves mathematically, but not what causes it or how it works. In his own words, he framed no hypotheses about the mechanism. Einstein figured out what Newton couldn't. In 1915, he published the general theory of relativity. The core idea is radical. Gravity isn't a force pulling objects together. It's a curvature of spacetime itself. Objects aren't being pulled. They're following the natural geometry of a curved four-dimensional structure. Think about what this means. When you drop a ball, nothing is pulling it downward. The ball is simply following the straightest possible path through curved space-time. That path happens to curve toward Earth's center because Earth's mass has warped the space-time around it. The ball isn't experiencing a force. It's moving freely along a geodesic, the space-time equivalent of a straight line. This isn't just philosophical wordplay. It has real, measurable consequences. Einstein's theory predicted things Newton's couldn't. The bending of light around massive objects, the precession of Mercury's orbit, gravitational time dilation, gravitational waves, black holes. All of these phenomena emerge naturally from the geometry of curved spacetime. None of them make sense if gravity is just a force. For over a century, every test has confirmed Einstein's view. From the 1919 solar eclipse observations to modern gravitational wave detectors, the evidence is overwhelming. Gravity is geometry, not force. Space and time aren't a static stage where events happen. They're dynamic, flexible, curved by mass and energy. Objects move through this curved spacetime, and their motion is determined by its geometry. This changes everything about how we understand the universe. Forces in physics are interactions mediated by particles. Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. But gravity isn't carried by particles. There's no exchange of gravitons, at least not in the way we think of force carriers in quantum field theory. Gravity is the shape of space-time itself. You might ask, why does it feel like a force? Why does it seem like Earth is pulling you down? We'll get to that. The answer is even stranger than you might think. Mass attracts mass. You've heard this your entire life. Probably said it yourself. It's how gravity is taught in schools. Earth's mass attracts your mass. The sun's mass attracts Earth's mass. Every object in the universe pulls on every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Newton's law of universal gravitation. It works. The math is correct. The predictions match observations. You can use it to calculate planetary orbits, design spacecraft trajectories, predict tides. For practical purposes, it's fine. But it's not what's actually happening. Mass doesn't attract mass, not in any direct, causal sense. There's no invisible rope connecting you to Earth, no mysterious action at a distance pulling objects together. Newton himself was troubled by this. How could objects separated by vast distances affect each other instantaneously without anything connecting them? He couldn't explain it. He just knew the mathematics worked. Einstein solved the mystery. Mass doesn't attract mass. Mass curves space-time. Other objects respond to that curvature. The mechanism is geometric, not attractive. Earth's mass curves the space-time around it. You exist within that curved space-time. You follow a geodesic through it. That geodesic happens to curve toward Earth's center, not because Earth is pulling you, but because that's the shape of space-time in Earth's vicinity. Consider two objects floating in space, far from any planet or star. According to Newton, they attract each other. Their mutual gravitational pull draws them together. But what's actually happening? Each object curves space-time around it. The curvature from each object affects the geodesic of the other. They move toward each other not because they're pulling on each other, but because the geometry of space-time around them directs their motion inward. The distinction matters. If gravity were truly a force, it would need to propagate somehow. Information about mass would need to travel from one object to another. In Newton's theory, this happens instantaneously. Move the sun and Earth would instantly feel the change in gravitational pull. But Einstein showed that's impossible. Nothing can travel faster than light, not even gravitational effects. Changes in space-time curvature propagate as gravitational waves at light speed. If the sun suddenly vanished, not that it can, but hypothetically Earth wouldn't immediately fly off into space. It would continue orbiting for roughly 8 minutes, the time it takes light to travel from the sun to Earth. Only when the gravitational wave carrying information about the sun's disappearance reached Earth would our planet's orbit change. The curvature would smooth out, and Earth would move in a straight line, no longer following a curved geodesic. This is fundamentally different from attraction. Attraction implies action at a distance, one object directly affecting another across empty space. Curvature is local. Mass curves spacetime in its immediate vicinity. That curvature extends outward, diminishing with distance. Other objects respond to the local geometry of spacetime where they are, not to distant masses directly. So stop thinking of gravity as attraction. Start thinking of it as geometry. Mass tells spacetime how to curve. Spacetime tells mass how to move. That's general relativity in one sentence. You live in spacetime, not space and time separately. Spacetime, a single, unified four-dimensional structure. This isn't a metaphor or a mathematical convenience. It's a description of physical reality. Before Einstein, space and time were considered separate. Space was the three-dimensional arena where things existed and moved. Up and down, left and right, forward and backward. Time was different. It flowed uniformly, the same for everyone everywhere. A cosmic clock ticking away, measuring the sequence of events. Space was where. Time was when. Fundamentally different. Einstein showed this is wrong. Space and time are woven together. You can't have one without the other. They're aspects of a single four-dimensional fabric. Every event in the universe happens at a specific location in space-time. Not just space and time separately. You can't specify where something happened without also specifying when. The where and when are intrinsically linked. Think about meeting a friend. You say, "Let's meet at the coffee shop." But that's not enough information. You also need to say when. "Let's meet at the coffee shop at 3 p.m. on Saturday." Now you've specified a point in space-time, 3 spatial dimensions, the location of the coffee shop. 1 time dimension, 3 p.m. on Saturday. Together, they define an event in space-time. This four-dimensional structure isn't just useful for scheduling. It's fundamental to how the universe works. When you move through space, you also move through time. When time passes, you're also moving through space-time. Even if you're sitting perfectly still in space, you're still moving through space-time because time is passing. You're traveling through the time dimension at 1 second per second. And here's where it gets interesting. Space-time isn't rigid. It's flexible. It can bend and curve. What causes it to curve? Mass and energy. Any object with mass or energy curves the space-time around it. The more massive the object, the more it curves space-time. Earth curves space-time. The sun curves space-time much more because it's much more massive. Even you curve space-time a tiny amount. Everything with mass or energy curves space-time to some degree. The usual analogy is a stretched rubber sheet. Place a bowling ball on it, and it creates a dip. Roll a marble near the bowling ball, and the marble curves toward it, following the slope of the depression. The marble isn't being pulled, it's following the curvature of the sheet. Similarly, Earth curves space-time around it. When you drop a ball, it follows the curvature of space-time toward Earth's center. But the analogy has limits. The rubber sheet is two-dimensional, bent in a third dimension. Space-time is four-dimensional, and it's not bending into some higher dimension. It's intrinsically curved. The curvature is a property of space-time itself, not a bending into something else. Also, in the rubber sheet analogy, we're using gravity to make the ball sink. That's circular when we're trying to explain gravity. So use the analogy for visualization, but don't take it too literally. The real concept is this. Space-time is a four-dimensional geometry that can be flat or curved. Mass and energy curve it. Objects move through it, following geodesics, the straightest possible paths in that curved geometry. When we say space-time is curved, we mean the rules of geometry are different. In flat space, parallel lines never meet. The angles of a triangle add up to 180 degrees. The shortest distance between 2 points is a straight line. But in curved space, parallel lines can converge or diverge. Triangle angles can add up to more or less than 180 degrees. The shortest path between 2 points is a curve called a geodesic. This isn't abstract mathematics, it's measurable reality. GPS satellites orbit Earth at high altitude, where space-time is less curved than on the surface. Time passes slightly faster for them than for us. The GPS system has to account for this time dilation or position calculations would drift by kilometers within hours. Every time you navigate with your phone, you're relying on corrections for space-time curvature. You're using general relativity without thinking about it. Space-time is the stage on which everything happens. But it's not a passive stage. It participates. It curves in response to mass and energy. That curvature affects how things move. And that's what we call gravity. Picture Earth floating in space. It's not sitting on anything. It's not suspended by strings. It's just there, surrounded by empty space. Except space isn't really empty. It's space-time, and Earth's presence changes it. Earth has mass, approximately 6 times 10 circumflex, 24 kilograms. That's a 6, followed by 24 zeros. Enormous. All that mass curves space-time in the region around Earth. The curvature is strongest near Earth's surface and gets weaker as you move farther away. But it extends outward indefinitely, diminishing but never quite reaching zero. What does this curvature look like? Imagine the geometry of space itself is warped. Distances aren't quite what you'd expect. Straight lines don't exist in the usual sense. Instead, there are geodesics, the paths representing the shortest distance between 2 points in curved space-time. Near Earth, those geodesics curve toward Earth's center. If you place an object near Earth, say a ball, and release it, the ball doesn't experience a downward pull. It simply moves along the geodesic. Because space-time is curved, that geodesic curves toward Earth. From your perspective, standing on Earth's surface, it looks like the ball is falling down. But from the ball's perspective, it's moving in a straight line through curved space-time. The Sun curves space-time far more than Earth because it's far more massive, about 333,000 times Earth's mass. The curvature extends throughout the solar system. Earth exists within that curved space-time. Earth's orbital path around the Sun isn't caused by an invisible rope pulling Earth inward. Earth is following a geodesic through the curved space-time created by the Sun's mass. Think of it this way. If space-time were flat, Earth would move in a straight line forever. But space-time isn't flat near the Sun. It's curved. Earth follows a geodesic through that curved space-time. That geodesic is a closed ellipse, an orbit. Earth is constantly falling toward the Sun, but also moving sideways fast enough that it keeps missing. Perpetual freefall. The same principle applies at every scale. The Moon orbits Earth following a geodesic through Earth's curved space-time. Satellites do the same. The International Space Station orbits roughly 400 kilometers above Earth's surface. At that altitude, space-time is still significantly curved by Earth's mass. The station follows a geodesic through that curved space-time, constantly falling toward Earth but moving sideways fast enough to stay in orbit. You can calculate the curvature mathematically. Einstein's field equations relate the curvature of space-time to the distribution of mass and energy. They're complex, 10 interrelated differential equations. But the principle is straightforward. Tell me the mass and energy distribution, and I can calculate the space-time curvature. Tell me the curvature, and I can predict how objects will move. The curvature isn't just in space. It's in space-time, all 4 dimensions. That means time is curved too. We'll get to that shortly. But the key point is this. Mass doesn't pull. Mass curves. Objects respond to that curvature by following geodesics. That's all gravity is. Geometry. Every object with mass curves spacetime. You curve spacetime around you. Your mass is small, so the curvature is tiny, utterly negligible. But it exists. If you could measure precisely enough, you'd detect it. Two people standing a meter apart curve space-time around them. The geodesics between them curve very slightly inward. If there were no other forces, they'd drift together over an absurdly long time. But the electromagnetic forces from air molecules, the floor beneath them, and everything else completely overwhelm this tiny effect. Only when masses become truly enormous does space-time curvature become significant. Planets, stars, black holes. These objects curve space-time enough to produce observable effects. Orbits, tides, gravitational lensing, time dilation, all consequences of curved space-time. This is how heavy objects warp the geometry around them. They don't reach out and pull. They change the shape of space-time itself, and everything else responds to that shape. This is going to feel completely backward. Your entire life, you've felt gravity pulling you down. When you stand, you feel Earth's gravity pulling you toward the ground. When you sit, you feel it pressing you into your chair. Down, down, down. A constant pull. Except that's not what's happening. You're not being pulled down at all. You're being pushed up, right now, this very moment. The ground beneath your feet is pushing you upward. That's what you feel. From the perspective of general relativity, freefall is the natural state. When you're falling, you're following a geodesic through curved spacetime. You're not experiencing any forces. You're weightless. Astronauts in orbit are in freefall. They float because they're following geodesics through curved spacetime. Nothing is pushing on them. But you're not in freefall. You're standing or sitting. Something is preventing you from following your natural geodesic through spacetime. That something is the ground, or your chair, or whatever is beneath you. The atoms in the ground are held together by electromagnetic forces. Those forces resist compression. When your body tries to follow its geodesic toward Earth's center, the ground stops you. It exerts an upward force. That force pushes you away from your natural geodesic. That upward force is what you feel as weight. Not a downward pull, an upward push. The sensation in your feet or in your seat. That's the electromagnetic forces from the ground or chair pushing on you, preventing you from falling. Think about it. If you jumped off a building, terrible idea, but stick with me, you'd feel weightless during the fall. You wouldn't feel gravity pulling you down. You'd feel nothing. You'd be in free fall, following your natural geodesic. The moment you hit the ground, you'd suddenly feel weight again. Not because gravity suddenly started pulling harder, because the ground suddenly started pushing up. An elevator provides a clearer example. Imagine you're in an elevator and someone cuts the cable. Horrifying scenario. As the elevator falls, you'd float inside it. You and the elevator are both in freefall, following the same geodesic. Relative to the elevator, you're weightless. You don't feel gravity pulling you down because nothing is preventing you from following your geodesic. Now imagine you're in a rocket in deep space, far from any planet or star. The rocket accelerates at 9.8 meters per second squared. The same acceleration you experience from Earth's gravity. You'd feel the floor of the rocket pushing up on your feet. You'd feel weight. From inside the rocket, you couldn't tell the difference between standing in the rocket and standing on Earth. Both feel the same. The equivalence principle. This is the key insight. Weight isn't the sensation of being pulled down. It's the sensation of being pushed away from your natural geodesic. On Earth, that push comes from the ground resisting your tendency to follow a geodesic toward Earth's center. In a rocket, it comes from the floor, accelerating upward through flat spacetime. Freefall and floating in zero gravity are equivalent. You can't tell the difference from inside your reference frame. Standing on Earth and accelerating in a rocket are equivalent. Again, no way to distinguish them from inside. This completely inverts the intuitive picture. We think of sitting still as the natural state and falling as requiring an explanation. But from the perspective of general relativity, falling is natural. Sitting still requires an explanation. That explanation is the electromagnetic forces from the ground preventing you from following your geodesic. You're not being pulled down, you're being pushed up. The ground is accelerating you upward through curved spacetime. That's what weight is, the resistance to free fall. You're sitting still, reading this, not moving, except you are moving. And not just because Earth is rotating or orbiting the Sun. You're accelerating right now, constantly. As long as you're in contact with the ground, or a chair or anything that prevents you from falling, you're experiencing acceleration. From the perspective of general relativity, acceleration means changing your path through spacetime. If you were in free fall, you'd follow a geodesic, a straight line through curved spacetime. But you're not in free fall. Something is preventing you from following that geodesic, the ground, the chair, whatever you're in contact with. Those objects are pushing you, changing your path through spacetime. That's acceleration. In flat spacetime, far from any mass, acceleration is straightforward. If you're floating motionless, you're following a straight line through spacetime, moving through the time dimension at 1 second per second. If a rocket fires and pushes you, you accelerate. Your path through space-time curves. That's acceleration. Near Earth, space-time is curved, a free fall. Geodesic curves toward Earth's center. If you're standing on the ground, you're not following that geodesic. The ground prevents you. It pushes you upward, away from the geodesic you'd naturally follow. Your path through space-time is constantly curving away from the freefall geodesic. That's acceleration. This isn't semantic wordplay. It's measurable. If you had an accelerometer, a device that measures acceleration, it would read 0 when you're in freefall. Jump off a diving board, and the accelerometer reads 0 during the fall. But standing on the ground, the accelerometer reads 9.8 meters per second squared upward. You're accelerating upward at that rate, constantly. This is why astronauts in orbit are weightless. They're not accelerating. They're following geodesics through curved spacetime. An accelerometer on the space station reads 0. The astronauts are in true freefall, the natural state of motion in curved spacetime. No acceleration, no weight. You, sitting in your chair right now, are accelerating upward at 9.8 meters per second squared. The chair is pushing you upward through curved spacetime. That push prevents you from following your natural geodesic. You experience that push as weight. This explains why all objects fall at the same rate in a vacuum. Galileo demonstrated this, supposedly by dropping objects from the Leaning Tower of Pisa. Whether he actually did that experiment is debated, but the principle is true. Drop a feather and a hammer in a vacuum, and they fall at the same rate. The Apollo 15 astronauts demonstrated it on the moon. Feather and hammer hit the ground simultaneously. In Newtonian physics, this is a curious coincidence. Gravitational force is proportional to mass, but acceleration produced by a force is inversely proportional to mass. The two effects exactly cancel. Heavy objects experience more gravitational force, but they also have more inertia-resisting acceleration. The result is the same acceleration regardless of mass. But why? Newton couldn't explain it. In general relativity, it's obvious. Objects aren't being pulled by a force proportional to their mass. They're following geodesics through curved space-time. The curvature doesn't care about an object's mass. All objects follow the same geodesics, so they all fall at the same rate, natural and inevitable. The only reason you're not falling right now is that the ground is accelerating you upward through curved spacetime. Stop that acceleration, remove the ground, and you'd immediately start following a geodesic. You'd fall, not because a force suddenly appeared, but because the upward acceleration preventing you from falling suddenly disappeared. This is one of the strangest aspects of general relativity. The natural state is free fall. The unnatural state is standing still. We have it completely backward in our everyday thinking. But the math and the observations confirm it. You're accelerating upward right now, and that's why you feel weight. Astronauts float in the International Space Station. They glide effortlessly from one module to another. Tools and equipment drift in midair. Water forms perfect spheres. Everything looks weightless. Many people assume this is because there's no gravity up there. The astronauts have escaped Earth's gravitational pull. They're beyond its reach. Completely wrong. The ISS orbits at an altitude of roughly 400 kilometers, about 250 miles above Earth's surface. At that altitude, Earth's gravitational field is still approximately 90% as strong as it is on the ground. The astronauts aren't beyond Earth's gravity. They're well within it. So why are they weightless? Because they're in free fall. The space station and everything inside it are falling toward Earth, constantly. They're following geodesics through the curved space-time created by Earth's mass. Those geodesics curve toward Earth's center. The station is falling, but it's also moving sideways at roughly 28,000 kilometers per hour, about 17,500 miles per hour, fast enough that as it falls toward Earth, Earth's curved surface falls away beneath it at the same rate. The station keeps missing Earth. It's in orbit. Orbit is perpetual free fall. You're falling, but you're moving sideways so fast that you never hit the ground. You keep falling around the curve of the planet. That's all an orbit is. And because the station is in free fall, everything inside experiences weightlessness. The astronauts are following the same geodesic as the station. They're falling at the same rate. So relative to the station, they don't move. They float, not because there's no gravity, but because they're embracing it completely. They're following the natural curvature of space-time without anything pushing on them. Free fall is the natural state. You experience the same thing when you jump. For the brief moment you're in the air, you're in free fall. You don't feel your weight. You're weightless. If the ground suddenly vanished and you kept falling, you'd feel exactly what the astronauts feel. True weightlessness. Not the absence of gravity, the presence of free fall. This is why the equivalence principle works. Free fall in a gravitational field is indistinguishable from floating in deep space with no gravity. You can't tell the difference from inside your reference frame. An astronaut in the ISS experiences the same weightlessness as an astronaut drifting in interstellar space far from any star. Both are in free fall. Both are following geodesics through space-time. Similarly, standing on Earth is indistinguishable from accelerating in a rocket in deep space. Both involve being pushed away from a geodesic. Both produce the sensation of weight. The mechanism is different: curved space-time versus flat space-time with rocket acceleration. But the experience is identical. This inverts our usual understanding. We think of Earth's surface as the baseline, the normal state. We think of astronauts as being in an unusual environment. But from the perspective of general relativity, the astronauts are in the natural state, free fall, following geodesics. We're the ones in an unusual state, being pushed upward by the ground, prevented from following our natural paths through space-time. Free fall isn't something that happens to you. It's what you do when nothing is interfering. When you're free to follow the geometry of space-time without obstruction, the astronauts aren't escaping gravity. They're experiencing it purely, following the geodesics that Earth's mass creates in space-time. If you could somehow turn off the electromagnetic forces holding Earth together, you'd fall through. You'd follow your geodesic all the way to Earth's center, oscillate through, and come back out the other side like a ball in a tunnel through a planet. You'd be in freefall the entire time, weightless. The only reason you can't do this is that electromagnetic forces stop you. The atoms in the ground resist compression. They push back. That's what keeps you on the surface. Not gravity holding you down, but electromagnetism holding you up. The natural state is freefall. Orbiting astronauts aren't escaping gravity. They're embracing it completely, and that's why they float. Time doesn't pass at the same rate everywhere. The stronger the gravitational field, the slower time passes. Not a perceptual effect. Not something that feels slower. Time actually passes at different rates, depending on where you are in a gravitational field. Take two identical atomic clocks. Put one on the ground. Carry the other up a mountain. Leave them there for a day. When you bring them back together, they'll show different times. The clock on the mountain ran slightly faster than the clock on the ground. The difference is tiny, measured in nanoseconds for typical mountains. But it's real, measurable, confirmed by countless experiments. Why? Because spacetime is more curved near Earth's surface than higher up. The stronger the curvature, the slower time passes. The clock on the mountain is farther from Earth's center. Spacetime is less curved there. Time passes slightly faster. The clock on the ground is closer to Earth's center. Spacetime is more curved. Time passes slightly slower. This is gravitational time dilation, a direct consequence of spacetime curvature, not some weird side effect, a fundamental property of how time works in curved spacetime. The effect becomes more dramatic near more massive objects. Near a neutron star, time passes roughly 30% slower than far from the star. Near a black hole's event horizon, time dilation becomes extreme. Time effectively stops from an outside observer's perspective, though someone falling in experiences nothing unusual at the horizon itself. You experience time dilation every day, without noticing it. Your head is slightly farther from Earth's center than your feet. Time passes slightly faster for your head than for your feet. The difference is absurdly small, roughly 10 trillionths of a second per day. You'll never notice it, but it's real. This was first measured precisely in 2010 by scientists at the National Institute of Standards and Technology. They placed two atomic clocks 33 centimeters apart, vertically. That's about 1 foot. The higher clock ticked slightly faster. The difference was around 90 trillionths of a second per day, measurable with sufficiently accurate clocks. The mathematics comes straight from general relativity. The closer you are to a massive object, the more space-time is curved. The more curvature, the slower time passes relative to regions of less curvature. It's not that clocks malfunction. It's not that something interferes with their mechanism. Time itself passes at different rates. This has profound implications. If you spent a year on the surface of a neutron star, which you couldn't survive but hypothetically, and then returned to Earth, you'd find that significantly more time had passed on Earth. You'd have traveled into Earth's future. Time dilation isn't symmetric when gravity is involved. The effect is reciprocal only in special relativity, where motion through flat space-time causes time dilation. If two people move relative to each other at high speed, each sees the other's clock running slow. That's the twin paradox setup. But with gravitational time dilation, there's no paradox. The person deeper in the gravitational field unambiguously experiences less time. This means time isn't universal. There's no cosmic clock ticking away uniformly for everyone. Time is local. It depends on where you are and what you're doing. Your time, your personal progression through the time dimension of space-time, depends on the curvature of space-time where you are. Time dilation has been confirmed by experiments with particles, atomic clocks, and astronomical observations. Pulsars, rapidly rotating neutron stars, emit pulses with extraordinary regularity. but the pulses are time-dilated by the neutron star's gravity. We measure this effect, and it matches predictions precisely. Time dilation is real. Clocks run slower closer to Earth. And this isn't a malfunction or an illusion. It's how time actually works in curved spacetime. Your phone knows where you are. Pull up a map, and there's a blue dot showing your location. Accurate to within a few meters. You navigate to unfamiliar places without thinking about it. Turn-by-turn directions guide you precisely. This technology is so reliable and ubiquitous that we take it for granted. It wouldn't work without Einstein. GPS, the Global Positioning System, relies on satellites orbiting Earth. There are roughly 30 of them at any given time, orbiting at altitudes around 20,000 kilometers, about 12,500 miles. Each satellite carries extremely accurate atomic clocks. These clocks broadcast time-stamped signals. Your phone receives signals from multiple satellites, calculates how long each signal took to arrive based on the timestamps, and uses that information to determine your position. The system requires incredible precision. The signals travel at the speed of light, roughly 300,000 kilometers per second. To pinpoint your location within a few meters, the system needs to measure signal travel times to within billionths of a second. The atomic clocks on the satellites are accurate enough. But there's a problem. General relativity. The satellites orbit high above Earth, where space-time is less curved than at the surface. Time passes faster up there, approximately 45 microseconds per day faster, due to gravitational time dilation. Meanwhile, the satellites are moving at high speed relative to Earth's surface, around 14,000 kilometers per hour. Special relativity predicts that moving clocks run slower. This causes the satellite clocks to lose roughly 7 microseconds per day. Net effect: the satellite clocks run about 38 microseconds per day, faster than clocks on Earth's surface. That's 38 millionths of a second. Doesn't sound like much, but light travels roughly 300 meters in 1 microsecond. In 38 microseconds, light travels about 11 kilometers. If the GPS system didn't correct for relativity, position calculations would drift by roughly 11 kilometers per day. Within hours, the system would be useless. The engineers who designed GPS knew this. They programmed the satellite clocks to tick at a slightly different rate than they would on Earth's surface. The clocks are intentionally set to run slower, so that once they're in orbit and time dilation effects kick in, they match the rate of clocks on the ground. The system also continuously updates using ground stations to correct for any drift. Every time you use GPS, you're relying on corrections for both gravitational time dilation from general relativity and velocity time dilation from special relativity. Without these corrections, navigation would fail within minutes. The system would accumulate errors so quickly it would become unusable. This isn't theoretical, it's practical engineering. GPS proves Einstein right every single day. Billions of devices worldwide depend on relativistic corrections. Your phone, your car's navigation system, aircraft autopilots, ships at sea, precision agriculture, surveying equipment, financial networks that timestamp transactions. All of it relies on accounting for the curvature of space-time. This is one of the most direct, everyday applications of general relativity. You don't need billion-dollar gravitational wave detectors or space telescopes to see relativity in action. You just need a phone with a map app. The fact that it works, that it gives you accurate directions, is proof that space-time is curved and time passes at different rates in different gravitational fields. Einstein published general relativity in 1915. GPS became fully operational in 1995. 80 years later, engineers had to account for effects predicted by a theory developed decades before the technology existed. The theory came first. The predictions were made. Then technology advanced to the point where those predictions became practically important. Without Einstein, GPS wouldn't work. That's not an exaggeration. The system fundamentally depends on understanding how space-time curvature affects time. Every time you navigate to a destination, you're using general relativity. You're trusting that Einstein's century-old equations correctly describe how time behaves near massive objects like Earth. And they do, perfectly. GPS satellites prove Einstein right. Every single day. Light has no mass. Photons, the particles of light, are massless. They travel at the speed of light, which only massless particles can do. So gravity shouldn't affect them, right? If gravity is a force that pulls on mass, and light has no mass, light should travel in perfectly straight lines, unaffected by gravitational fields. Except that's not what happens. Light bends around massive objects. We've observed it countless times. Starlight bends when it passes near the sun. Light from distant galaxies bends when it passes near galaxy clusters. Light even bends slightly when it passes near Earth, though the effect is too small to measure with current technology. In Newton's theory, this made no sense. Gravity pulls on mass. Light has no mass. Therefore, gravity shouldn't affect light. When Einstein first predicted that light would bend near massive objects, it was a radical claim. It contradicted everything physics knew at the time. But remember, gravity isn't a force. It's not pulling on anything. Gravity is the curvature of spacetime. And light, like everything else, travels through spacetime. When spacetime is curved, light follows that curvature. Think about it this way. Light always travels in straight lines. Always. But straight line has a specific meaning in general relativity. It means a geodesic, the shortest path through space-time. In flat space-time, far from any mass, geodesics are what we normally call straight lines. A beam of light travels in a perfectly straight line forever. But near a massive object, space-time is curved. Geodesics through curved space-time are themselves curved when viewed from a distance. Light still travels along geodesics, still taking the shortest path through space-time. But because space-time itself is curved, that shortest path curves around the massive object. The sun curves space-time around it. A beam of light passing near the sun follows a geodesic through that curved space-time. The path curves, not because the sun is pulling on the light, but because the geometry of space-time is curved. The light is still going straight from its own perspective, following the local geometry. But from our perspective, far away, the light's path bends. This was first observed in 1919 during a solar eclipse. Arthur Eddington led expeditions to observe stars near the sun during the eclipse when the sun's glare didn't overwhelm the starlight. The stars appeared slightly displaced from their known positions. The sun's gravity was bending the starlight passing near it. The displacement was small, about 1.75 arcseconds, less than 1/2000th of a degree, but it was measurable and matched Einstein's predictions. This observation made Einstein world famous overnight. Headlines proclaimed that Newton had been overthrown. That's overstating it. Newton's theory still works brilliantly for most purposes. But Einstein's theory explains something Newton's couldn't: why light bends near massive objects. The amount of bending depends on the mass of the object and how close the light passes to it. Light grazing the sun's surface bends by those 1.75 arcseconds. Light passing farther away bends less. Light passing very close to a more massive object like a neutron star or black hole bends much more dramatically. Near a black hole, light can be bent into orbit. There's a region called the photon sphere where light orbits the black hole in circular paths. Light traveling outward from inside the photon sphere can curve back and fall into the black hole. Only light traveling exactly radially outward can escape. This creates strange visual effects. If you orbited just outside the photon sphere and looked around, you could see the back of your own head. Light from you would orbit the black hole and come back to your eyes. Light bending around massive objects isn't just a curiosity, it's a tool. Astronomers use it constantly. We call it gravitational lensing, and it's revolutionized how we observe the universe. More on that shortly. The key point is this: light has no mass, but gravity still affects it. Not because gravity pulls on mass, because gravity is the curvature of space-time, and light travels through space-time. Curves space-time, and light curves with it. Simple, elegant, confirmed by every observation we've made. Massive objects bend light. We've established that. But it's not just an interesting effect. It's an incredibly powerful tool. When a massive object sits between us and a distant light source, it acts like a lens. The massive object's gravity bends light from the distant source, focusing it toward us. We call this gravitational lensing. Think of a glass lens. It bends light rays, bringing them to a focus. You can use a lens to magnify distant objects, making them appear larger and brighter. Gravitational lensing does the same thing, except the lens isn't glass. It's the curved space-time around a massive object. A galaxy cluster. A galaxy, even a star, can act as a gravitational lens. The effect comes in several varieties. Strong lensing happens when a very massive object, like a galaxy cluster, lies almost directly between us and a distant galaxy. The foreground cluster bends light from the background galaxy so much that we see multiple images of the same galaxy. Sometimes the galaxy gets stretched into arcs, or even complete rings, called Einstein rings. The background galaxy is effectively smeared around the lensing object. These multiple images aren't illusions. They're real light from the same object taking different paths around the lensing mass. Light travels along geodesics through curved space-time. Near a massive object, there can be multiple geodesic paths connecting the same 2 points. Light takes all available paths. We see separate images for each path. Weak lensing is more subtle. The background galaxy doesn't get turned into multiple images. Instead, it gets slightly distorted, stretched into an ellipse. A single galaxy's distortion might be unnoticeable, but when you observe thousands of background galaxies, you see a pattern. All the galaxies are stretched slightly in the same direction, pointing toward the lensing mass. By analyzing this pattern, astronomers can map the distribution of mass in the foreground, including dark matter. This is huge. Dark matter doesn't emit light. We can't see it directly, but it has mass, so it curves space-time. Gravitational lensing lets us see dark matter's effects. Galaxy clusters contain enormous amounts of dark matter, far more than ordinary matter. By studying how background galaxies are lensed, we map where the dark matter is. We've created detailed maps of dark matter distribution in galaxy clusters this way. Microlensing is different still. If a star passes between us and a more distant star, the foreground star's gravity can briefly magnify the background star's light. The background star brightens temporarily, then returns to normal as the alignment changes. The effect lasts days to weeks depending on the masses and speeds involved. Microlensing has been used to discover exoplanets. If a star with planets passes in front of a background star, the star's lensing effect creates a brightness curve. If a planet orbits the lensing star, it adds a small spike to that curve. By analyzing these spikes, astronomers have detected planets orbiting distant stars. Planets we could never see directly, but whose gravity subtly affects the lensing. Gravitational lensing magnifies distant objects, letting us see things otherwise too faint or too far away. Some of the most distant galaxies ever observed were magnified by foreground galaxy clusters. Without the lensing, we wouldn't be able to detect them. The cluster acts like a natural telescope, amplifying light from objects billions of light-years behind it. The Hubble Space Telescope has captured stunning images of gravitational lensing, distant galaxies stretched into arcs and rings around massive foreground clusters, multiple images of the same galaxy appearing in different parts of the sky. These aren't artistic effects, they're real observations showing space-time curvature in action. We also use lensing to weigh objects. The amount of lensing depends on the lensing object's mass. By measuring how much background galaxies are distorted or magnified, we can calculate the foreground object's mass. This works even if we can't see the lensing object directly. Dark matter can be weighed this way. We can't see it, but we can measure how much it bends light. That tells us how much mass is there. Gravitational lensing confirms general relativity's predictions. The amount of bending matches Einstein's equations precisely. If gravity worked differently, the lensing effects would be different. Every observation confirms that space-time curvature is real and behaves exactly as Einstein predicted. This isn't just academic. Gravitational lensing is a standard tool in modern astronomy. Every major telescope uses it. Every deep sky survey relies on it. We've gone from barely detecting the effect in 1919 to using it routinely to study the universe's structure, dark matter distribution, and the most distant objects in existence. Light bends around massive objects, and we've turned that bending into one of the most powerful observational techniques in all of astronomy. Newton's theory of gravity had a problem he couldn't solve. Gravity in his equations acted instantaneously across any distance. Move the Sun and Earth would feel the change immediately. No delay, no travel time, instant action at a distance. Newton knew this was troubling. How could objects separated by millions of kilometers affect each other with no mechanism, no medium, nothing connecting them? He couldn't explain it. He called it absurd, but acknowledged the math worked. So the problem remained unsolved for over 200 years. Einstein solved it. In general relativity, gravity isn't a force transmitted between objects. It's the curvature of space-time. Changes in that curvature don't propagate instantaneously. They travel as waves in space-time itself. Gravitational waves. And those waves travel at exactly the speed of light. The speed of light isn't really about light. It's the speed of causality. The maximum speed at which information or influence can propagate through space-time. Nothing can travel faster. Not light, not gravitational effects, not anything. The speed of light is built into the structure of space-time itself. If the Sun suddenly vanished, which it can't, but hypothetically Earth wouldn't immediately fly off into space, it would continue orbiting for about 8 minutes and 20 seconds, the time it takes light to travel from the Sun to Earth. During those 8 minutes, Earth would have no way of knowing the Sun was gone. The space-time curvature near Earth would still reflect the Sun's presence because the change in curvature hasn't arrived yet. Only when the gravitational wave carrying information about the Sun's disappearance reached Earth would our orbit change. The curvature would smooth out. Earth would stop following an elliptical geodesic and start following a straight line through flatter space-time. We'd fly off into interstellar space, but not instantly, after an 8-minute, 20-second delay. This is fundamentally different from Newton's gravity. In Newton's theory, gravitational effects are instantaneous. Move a mass, and every other mass in the universe feels the change immediately. Einstein showed that's impossible. Changes in gravitational fields propagate at light speed, no faster. This prediction was confirmed in 2017 in a spectacular way. LIGO and Virgo, gravitational wave detectors in the United States and Europe, detected gravitational waves from 2 neutron stars colliding. At almost exactly the same time, telescopes detected a gamma-ray burst from the same event. The gravitational waves and electromagnetic waves arrived within 1.7 seconds of each other after traveling 130 million light-years. This proved that gravitational waves travel at the speed of light to extraordinary precision. If gravity traveled even slightly faster or slower than light, the waves would have arrived at noticeably different times after such a long journey. But they arrived together. Gravity and light propagate at the same speed through spacetime. Why exactly the speed of light? Because that's the speed of causality. It's built into the geometry of space-time. Space-time has a structure, a metric, that determines the relationships between space and time. That structure includes a maximum speed for cause and effect. We call it the speed of light because light travels at that speed, but it's really the speed of space-time itself. Massless particles like photons travel at this speed. Gravitational waves, which are ripples in space-time itself, also travel at this speed. Anything without mass that propagates through space-time travels at this fundamental cosmic speed limit. This has profound implications. It means the gravitational field of an object extends outward at light speed as the object moves. If a star suddenly appeared in previously empty space, its gravitational influence wouldn't instantly fill the surrounding region. It would expand outward as a wave traveling at light speed. Observers far away wouldn't feel the new star's gravity until the wave reached them. It also means there's no such thing as instantaneous action at a distance. Everything that happens takes time to affect distant regions. The universe has a built-in delay. Information can't travel faster than light. Gravitational effects can't propagate faster than light. This preserves causality. It prevents paradoxes where effects precede causes. Newton's instantaneous gravity violated this principle. Though Newton didn't know it at the time, Einstein's gravity respects it. Gravitational changes propagate as waves at light speed, no faster, and we've measured it directly. The speed of gravity equals the speed of light. Exactly. Einstein predicted gravitational waves in 1916, just months after publishing general relativity. The equations said that accelerating masses should produce ripples in space-time itself. These ripples would travel outward at the speed of light, carrying energy away from their source, waves in the fabric of space and time. It sounded like science fiction. Space-time isn't a physical substance you can touch or see. How could it have waves? But the mathematics was clear. If space-time is a dynamic geometry that can be curved by mass, it should also support waves, oscillating curvature propagating through space. For decades, gravitational waves remained theoretical. Einstein himself thought they'd be far too weak to ever detect. The effect of a passing gravitational wave is incredibly small. It stretches and squeezes space alternately in perpendicular directions. But the stretching is measured in fractions of the width of an atomic nucleus over distances of kilometers. Detecting something that small seemed impossible. In the 1970s, indirect evidence appeared. Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. They measured the orbital period over several years and found it was decreasing. The two stars were spiraling closer together. They calculated how much energy the system should be losing if it was radiating gravitational waves. The rate matched perfectly. The orbit was decaying at exactly the rate predicted by general relativity if the system was emitting gravitational waves. This was indirect detection. They didn't measure the waves themselves. They measured the effect of energy loss on the orbit. But it confirmed that gravitational waves carry energy and that compact objects emit them when they accelerate. Hulse and Taylor won the Nobel Prize in 1993, but direct detection required building an instrument of almost incomprehensible sensitivity. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of two facilities separated by 3,000 kilometers, one in Louisiana, one in Washington state. Each facility has two arms, 4 kilometers long, arranged in an L shape. Laser beams travel back and forth along these arms, bouncing between mirrors. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the perpendicular direction. One arm gets slightly longer, while the other gets slightly shorter. The lasers detect this by measuring tiny shifts in the interference pattern when the beams recombine. The precision required is staggering. When LIGO made its first detection, The change in arm length was about 1/10,000th the diameter of a proton. That's like measuring the distance to the nearest star to within the width of a human hair. The engineering challenges were enormous. The mirrors had to be isolated from vibrations. The lasers had to be stabilized to extraordinary precision. The vacuum chambers had to be among the best vacuums ever created. On September 14, 2015, both LIGO detectors picked up a signal. A gravitational wave had swept through Earth. The waveform was distinctive, a chirp, rapidly increasing in frequency and amplitude, then cutting off suddenly. By analyzing the signal, scientists determined it came from two black holes spiraling into each other, 1.3 billion light-years away. The black holes had masses of 29 and 36 times the Sun's mass. As they orbited, they emitted gravitational waves, losing energy, spiraling closer and faster. In the final fraction of a second, they merged. The final black hole had 62 solar masses. 3 solar masses, about the mass of 600 quadrillion Earths, had been converted entirely into gravitational wave energy in that brief moment. The power output during the merger was about 50 times greater than all the stars in the observable universe combined. For that fraction of a second, the collision released more energy in gravitational waves than all the light from every star in the universe. Hard to comprehend. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are black hole mergers. Some are neutron star mergers. Each detection confirms Einstein's century-old predictions. Gravitational waves exist. They travel at light speed. They carry energy. Their properties match general relativity's equations exactly. This opened a new era of astronomy. For the first time, we're observing the universe with something other than light. Gravitational waves pass through matter almost unimpeded. They carry information about events we could never see with traditional telescopes. The insides of neutron star collisions, the final moments before black holes merge. Potentially, the very early universe moments after the Big Bang. Gravitational waves are real. Spacetime really does ripple. We've detected those ripples. We've measured them. We've used them to observe cosmic events impossible to see any other way. Einstein was right. Again, black holes have a reputation. They're portrayed as cosmic vacuum cleaners, sucking in everything nearby. Unstoppable monsters devouring stars and planets. Get too close, and you're doomed, pulled inexorably inward. This is misleading. Black holes don't suck. They don't pull any harder than any other object of the same mass. If you replace the Sun with a black hole of the same mass, which can't happen because the Sun isn't massive enough to become a black hole, Earth's orbit wouldn't change. We'd continue orbiting at the same distance. We'd freeze because the black hole wouldn't radiate light and heat, but we wouldn't get sucked in. Black holes are just mass, extremely concentrated mass, but mass nonetheless. They curve space-time around them. Other objects respond to that curvature by following geodesics, the same as around any massive object. The only difference is how close you can get. With a normal star, you can't get closer than the star's surface. If you tried to orbit closer, you'd crash into the star. The star's physical matter is in the way, but a black hole's matter has collapsed inside the event horizon. There's no physical surface to crash into. You can get much closer to the center of mass, and space-time curvature gets stronger as you get closer. That's what makes black holes dangerous. Not that they pull harder, but that you can get closer to the center of mass, where tidal forces become extreme. Tidal forces are differences in gravitational pull across an object. Near Earth, tidal forces are gentle. Your head and feet experience nearly the same gravitational pull. Near a black hole, the difference becomes savage. If you fell toward a black hole feet first, your feet would be closer to it than your head. The pull on your feet would be stronger. You'd be stretched vertically and compressed horizontally. As you got closer, the stretching would intensify. Eventually, you'd be torn apart. Spaghettification, a real physics term. For a small black hole, a few solar masses, spaghettification happens before you reach the event horizon. You'd be ripped apart in the approach. For a supermassive black hole, millions or billions of solar masses, the event horizon is so far from the center that tidal forces at the horizon are relatively gentle. You could cross the event horizon intact. You'd only get spaghettified later as you fell closer to the singularity. But at a safe distance, a black hole behaves just like any other mass. If you orbit far enough away, you're fine. You follow a geodesic through curved space-time. The geodesic might be an orbit, and you stay in orbit indefinitely. Just like satellites orbit Earth, or planets orbit the Sun, our galaxy has a supermassive black hole at its center, Sagittarius A, with a mass of about 4 million suns. Stars orbit it. Some get quite close. One star, S2, has an orbital period of about 16 years and gets as close as 17 light hours from the black hole. At its closest approach, it travels at about 2.5% of light speed. It's been tracked for decades. The event horizon is the defining feature of a black hole. It's the boundary where escape becomes impossible. Cross it, and you can never come back. All paths lead inward. There's no way out. But what exactly is it? Not a physical surface, not a barrier you could touch. It's a boundary in space-time geometry, a point of no return where the structure of space-time itself changes fundamentally. Think about geodesics. Far from a black hole, geodesics can point in any direction, outward, inward, sideways. You have freedom of motion. You can travel away from the black hole if you want. As you get closer, space-time becomes more curved. Some geodesics still point outward. You can still escape, though it takes more effort, more energy. At the event horizon, something changes. All future-directed time-like geodesics point inward. There are no geodesic paths that lead outward. The geometry of space-time is so severely warped that every possible future path takes you closer to the center. You can't stand still. You can't move sideways indefinitely. You can't escape. The only direction time flows is inward. This is hard to visualize because it involves time as well as space. Inside the event horizon, the inward direction becomes time-like. The radial direction toward the singularity becomes unavoidable in the same way that moving forward in time is unavoidable. Just as you can't avoid moving into the future, you can't avoid moving toward the singularity once you're inside the event horizon. Outside the event horizon, the center of the black hole is a place, a spatial location. You can choose to move toward it or away from it. Inside the event horizon, the singularity isn't a place. It's a moment in your future, a time you will inevitably reach. You can no more avoid hitting the singularity than you can avoid tomorrow coming. The size of the event horizon depends on the black hole's mass. For a non-rotating black hole, the radius is called the Schwarzschild radius. It's proportional to mass. A black hole with the sun's mass would have an event horizon about 3 kilometers in radius. A black hole with 10 solar masses would have a radius of about 30 kilometers. A supermassive black hole with 1 billion solar masses would have a radius of about 3 billion kilometers, larger than the orbit of Saturn. Nothing special happens at the event horizon itself from a local perspective. If you were falling into a black hole, you'd cross the event horizon without feeling anything unusual. No barrier, no sudden change. Locally, space-time seems fine. You're in free fall, following a geodesic. From your perspective, you just keep falling. But from an outside observer's perspective, you never quite reach the horizon. As you approach, time dilation becomes more extreme. Your clock slows relative to the outside universe. Light from you becomes increasingly redshifted. You appear to slow down approaching the horizon asymptotically. You never quite cross it from the outside view. You appear frozen just above the horizon, your image fading as the light redshifts beyond visibility. This isn't a contradiction, it's a perspective difference. From your perspective, you cross the horizon in finite time. From an outside perspective, the crossing takes infinite time. Both are correct from their respective reference frames. Time is relative. What's simultaneous for you isn't simultaneous for someone far away. Inside the event horizon, the geometry becomes strange. All paths lead to the singularity. You can point your rocket engines outward and fire them at maximum thrust. You'll only slow your approach slightly. You can't stop. You can't reverse. The singularity is in your future, and futures are unavoidable. Light emitted from inside the event horizon can't escape either. It follows geodesics, and all geodesics point inward. Light aimed outward might slow its inward fall temporarily, but it will eventually reach the singularity. That's why the region is black. No light gets out, no information escapes. The event horizon is the boundary where space-time curvature becomes so extreme that escape is geometrically impossible. Not difficult, impossible. The structure of space-time itself forbids it. It's a point of no return defined purely by geometry, and once you cross it, your fate is sealed. You will reach the singularity. It's not a matter of if, but when. Spaghettification sounds like a joke. It's not. It's the actual term physicists use to describe what happens when tidal forces become extreme near a black hole or neutron star. You get stretched vertically and compressed horizontally until you resemble spaghetti. Long, thin, and definitely dead. Tidal forces are caused by differences in gravitational pull across an object. On Earth, the Moon pulls slightly harder on the side of Earth facing it than on the far side. This difference creates tides in the oceans. The effect is gentle. Water rises and falls by a few meters twice a day, hardly noticeable on land. Near a black hole, tidal forces are catastrophic. If you fell toward a black hole feet first, your feet would be closer to it than your head. Space-time curvature is stronger closer to the center. Your feet follow a geodesic that curves more sharply than your head's geodesic. The result is that your feet accelerate faster than your head. You get stretched. At the same time, geodesics converge toward the center of mass. Your left side and right side are following geodesics that point slightly inward, toward the black hole's center. This compresses you horizontally. You're simultaneously stretched lengthwise and squeezed crosswise. Initially, the effect is small, mildly uncomfortable, but as you fall closer, it intensifies. Your feet pull away from your head. Your torso compresses. Eventually, the forces exceed what your body can withstand. Bones break. Tissues tear. You're pulled apart. For a small black hole, a few solar masses, this happens well before you reach the event horizon. Let's say the black hole has 10 solar masses. The event horizon is about 30 kilometers in radius. But lethal tidal forces appear much farther out, hundreds of kilometers away. You'd be torn apart long before crossing the horizon. For a supermassive black hole, things are different. A black hole with 1 billion solar masses has an event horizon roughly 3 billion kilometers in radius. Space-time curvature at the horizon is actually quite gentle because you're still very far from the center of mass. Tidal forces at the horizon might be survivable. You could cross the event horizon intact. Of course, you'd still die eventually. Inside the horizon, you fall toward the singularity. As you get closer, tidal forces increase. Eventually, they become lethal. But for a supermassive black hole, you might survive for hours inside the event horizon before tidal forces rip you apart. That's cold comfort, but it's technically true. The term spaghettification was coined because the effect makes you look like a strand of pasta, long and thin. Your atoms get pulled apart. First, your body separates into chunks. Then those chunks separate into molecules. Then molecules separate into atoms. Then atoms themselves get torn apart, electrons ripped from nuclei. Near the singularity, assuming general relativity describes it accurately, which it probably doesn't at that scale, tidal forces would become infinite. Infinite stretching, infinite compression. Everything gets shredded down to the most fundamental constituents, whatever those are. Quarks, maybe, or something even more basic. We don't know because we don't have a quantum theory of gravity. Neutron stars also produce extreme tidal forces, though less extreme than black holes. Fall toward a neutron star and you'd experience similar spaghettification, stretched and compressed until torn apart. The surface gravity of a neutron star is about 200 billion times Earth's. The tidal forces a few kilometers from the surface are lethal. This isn't hypothetical. Tidal forces are real, measurable and thoroughly understood within general relativity. We've observed their effects on stars that pass too close to black holes. The star gets stretched into a long stream of gas, part of it falling into the black hole, part escaping. These tidal disruption events release enormous amounts of energy, visible as bright flares that fade over weeks or months. Spaghettification is real. It's what happens when you get too close to an object with extreme space-time curvature. Tidal forces pull you apart, literally, and there's nothing you can do to stop it. The geometry of space-time itself is tearing you into strands. Black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. This radiation carries energy away, causing the black hole to lose mass and shrink over time. Black hole evaporation. The mechanism involves quantum mechanics. According to quantum field theory, empty space isn't truly empty. Particle-antiparticle pairs constantly pop into existence, then annihilate each other almost immediately. Virtual particles. Normally, this doesn't lead to anything observable. The pairs appear and disappear too quickly. But near a black hole's event horizon, something different can happen. A particle-antiparticle pair appears right at the horizon. One particle falls into the black hole. The other escapes. From outside, it looks like the black hole is emitting particles, Hawking radiation. The energy for this radiation comes from the black hole's mass. Each emitted particle carries energy away. The black hole loses mass. Over time, it shrinks. Eventually, it evaporates completely. For large black holes, this process is incredibly slow. A black hole with the sun's mass would take about 10 circumflex 67 years to evaporate. That's a 1 followed by 67 zeros. For comparison, the universe is only about 10 circumflex 10 years old, so a solar mass black hole would take vastly longer than the current age of the universe to evaporate. For supermassive black holes, evaporation times are even longer, far beyond any meaningful timescale. But for tiny black holes, if they exist, evaporation could be fast. A black hole with the mass of a mountain would evaporate in about 1 billion years. A black hole with the mass of a car would explode in a fraction of a second. We've never observed Hawking radiation directly. It's far too weak for current technology. But the prediction is widely accepted because it follows naturally from combining quantum mechanics with general relativity near the event horizon. Here's where the paradox comes in. According to general relativity, information that falls into a black hole is lost. It can't escape. The black hole's interior is causally disconnected from the outside universe. Whatever information fell in, the quantum state of particles, the arrangement of matter, all of it is gone. But according to quantum mechanics, information can't be destroyed. It can be scrambled, mixed up, transformed, but it must be preserved in some form. The evolution of quantum systems is reversible. Given complete information about a system at one time, you can calculate its state at any other time, past or future. These two principles conflict. If information falls into a black hole, and the black hole evaporates via Hawking radiation, what happens to the information? Does it come out in the radiation, or is it lost forever? Hawking originally argued that information is lost. Black holes are the one place where quantum mechanics breaks down. This caused an uproar. For decades, physicists debated the black hole information paradox. Some argued information must be preserved, encoded somehow in the Hawking radiation. Others argued information is genuinely lost. In the early 2000s, Hawking conceded he was probably wrong. He suggested information might be encoded in subtle correlations in the Hawking radiation. But exactly how this works mathematically remains unclear. The radiation coming out seems thermal, random, carrying no information. Yet somehow, the information must be preserved. Recent work suggests the information might be encoded at the event horizon itself, in a holographic manner. The holographic principle proposes that all information about a volume of space can be encoded on its boundary surface. For a black hole, the horizon acts as this boundary. Information about everything that fell in might be preserved in the structure of the horizon, gradually released as the black hole evaporates. This would preserve quantum mechanics, but requires a deeper understanding of quantum gravity. We don't have that yet, so the information paradox remains one of the deepest puzzles connecting quantum mechanics, gravity, and information theory. Black holes evaporate. That's almost certain. But what happens to the information they swallowed? That question is still open, and the answer will likely require a complete theory of quantum gravity, something we don't yet have. Information is physical, not an abstract concept, but something real with physical consequences. In quantum mechanics, information is encoded in the quantum state of a system, the positions, momenta, spins of all particles, the relationships between them. All of it constitutes information about the system. A fundamental principle of quantum mechanics is unitarity. The evolution of quantum states is reversible. If you know the quantum state of a system now, you can calculate its state at any past or future time. Information is never lost, only transformed. You can scramble it, spread it out, make it practically impossible to recover. But in principle, it's always there. This principle has been tested extensively. Every quantum system we've studied preserves information. Particles collide and produce other particles, but the total information is conserved. Complex chemical reactions scramble information across molecules, but it's not lost. Stars burn fuel for billions of years, but the information about the initial atoms is, in principle, preserved in the final state of the star and its radiation. Then there are black holes. According to general relativity, anything that falls past the event horizon is gone, causally disconnected from the outside universe. The information about what fell in, the quantum states of particles, the arrangements of atoms, all of it disappears behind the horizon. As the black hole evaporates through Hawking radiation, it shrinks. Eventually, it vanishes completely. What happened to all the information that fell in over its lifetime? Did it escape in the radiation, or was it destroyed when the black hole disappeared? If information is destroyed, quantum mechanics is violated. Unitarity breaks down. The universe would have amnesia about what fell into the black hole. This would be revolutionary, overturning one of the most fundamental principles of physics. But it seems unavoidable from the perspective of general relativity. If information escapes in the Hawking radiation, we need an explanation for how. The radiation appears thermal, random, carrying no information about what fell in. It's like the radiation from a hot stove, completely characterized by temperature. No details about the fuel burned or the structure of the stove. How could information be encoded in something so featureless? This is the information paradox. Two fundamental theories, general relativity and quantum mechanics, give contradictory answers. One says information is lost. The other says it can't be. Stephen Hawking originally argued information is lost. In 1997, he made a famous bet with physicists John Preskill and Kip Thorne about whether information is preserved. Hawking bet it was lost. In 2004, he conceded, admitting he was probably wrong. But the concession was based more on theoretical arguments than definitive proof. The leading resolution involves the holographic principle. This principle states that all information about a three-dimensional volume can be encoded on its two-dimensional boundary, like a hologram, where a 3D image is encoded on a 2D surface. For a black hole, the event horizon is the boundary. Information about everything that fell into the black hole might be encoded in quantum details of the event horizon itself. As the black hole evaporates, this information is gradually released in the Hawking radiation. The radiation only appears thermal if you ignore extremely subtle correlations. Those correlations carry the information. This preserves unitarity. Information isn't lost. It's scrambled in extraordinarily complex ways, spread across the Hawking radiation emitted over the black hole's entire lifetime. Recovering the information would be practically impossible, but theoretically possible. But this explanation requires quantum gravity. General relativity alone can't describe the quantum state of the event horizon. We need a theory that combines quantum mechanics with space-time curvature, string theory, loop quantum gravity, or something else. We don't have a complete, tested theory yet. So, the information paradox remains open. We're fairly confident information is preserved. Most physicists believe unitarity holds, but we don't fully understand the mechanism. We don't have the mathematics worked out completely. That requires solving quantum gravity, one of the biggest unsolved problems in theoretical physics. Information can't be destroyed. Probably, almost certainly. But proving it rigorously requires understanding how quantum mechanics and gravity work together at the deepest level. We're not there yet. General relativity allows for some truly bizarre space-time geometries. Among the strangest are wormholes, tunnels connecting distant regions of space-time, shortcuts through the universe, travel into one end and emerge from the other, potentially light-years away. Wormholes appear in solutions to Einstein's equations. They're mathematically consistent. The equations don't forbid them. The first wormhole solution was found by Carl Schwarzschild in 1916, just months after Einstein published General Relativity. Ironically, the Schwarzschild solution describes a black hole, but it includes a mathematical extension connecting to another region of space-time. This extension is called the Einstein-Rosen bridge, a tunnel connecting two black holes, or a black hole and a white hole, the time-reversed equivalent of a black hole. Matter falls into a black hole. In theory, it could emerge from a white hole elsewhere, a wormhole. The problem is that these early wormhole solutions were unstable. They collapsed too quickly for anything to pass through. You'd need to travel faster than light to traverse the wormhole before it pinches off, and the collapse would create a singularity, destroying anything inside. Later, physicists found other solutions. In 1988, Kip Thorne and colleagues showed that wormholes could theoretically be made traversable if they're held open by exotic matter. Exotic matter has negative energy density. It gravitationally repels instead of attracts. Such matter violates normal energy conditions, but quantum mechanics allows it in small amounts under certain circumstances. The Casimir effect demonstrates this. Two metal plates placed very close together in a vacuum experience a small attractive force. This happens because the vacuum between the plates has slightly negative energy density due to quantum fluctuations. The effect is tiny and only works on microscopic scales, but it proves negative energy density is possible. Whether enough exotic matter can exist to hold a macroscopic wormhole open is unknown. The amounts required are enormous. It might be physically impossible to collect or create that much exotic matter, or there might be unknown quantum effects that prevent it. Even if wormholes can be constructed, there are other problems. One is causality. A wormhole, connecting distant regions of space, could potentially be manipulated to connect different times. This creates the possibility of closed time-like curves, paths through spacetime that loop back to the past. Time travel. Time travel raises paradoxes. If you travel back and prevent your own birth, do you still exist to travel back? These paradoxes might be resolved in various ways. Maybe the universe doesn't allow configurations that lead to paradoxes. Maybe quantum mechanics prevents them. Maybe information going through a wormhole gets destroyed or scrambled. We don't know. Stephen Hawking proposed the chronology protection conjecture. The laws of physics conspire to prevent time travel, forbidding closed time-like curves. Perhaps quantum effects destroy any attempt to create a time machine. Perhaps the exotic matter needed for a wormhole can't be arranged in a configuration that allows time travel. The conjecture remains unproven. Despite these issues, wormholes are taken seriously in theoretical physics. They're solutions to Einstein's equations. They might exist. They help us explore the limits of general relativity and understand what's possible in curved spacetime. Some physicists speculate wormholes might be created naturally in extreme conditions. The early universe, high-energy particle collisions, or the cores of black holes. Microscopic wormholes might constantly form and dissolve in the quantum foam of spacetime at the Planck scale, far too small to be detected or used. Whether large, traversable wormholes exist or can be created remains unknown. The mathematics allows them under certain conditions, but those conditions might be physically unrealizable. We need a complete theory of quantum gravity to know for sure. Wormholes might be possible. They're not forbidden by general relativity. But practical wormholes that you could actually use to travel across the universe or through time, that requires exotic matter, stable configurations, and physics we don't fully understand. They're fascinating theoretical possibilities. Whether they're real is an open question. Black holes are regions where nothing can escape. White holes are the opposite, regions where nothing can enter. Matter and light can only leave, never fall in. Time-reversed black holes. They appear in the mathematics of general relativity. The Schwarzschild solution, which describes a non-rotating black hole, actually includes two regions. One is the familiar black hole, with its event horizon. The other is a white hole, connected through a wormhole. Mathematically, they're equally valid solutions to Einstein's equations. A white hole would have a boundary like an event horizon, but reversed. At a black hole's event horizon, all future-directed paths point inward. At a white hole's boundary, all past-directed paths point inward, which means all future-directed paths point outward. You can leave, but you can never enter. Matter and radiation would pour out of a white hole continuously. From outside, a white hole would look strange. It would emit light and matter unpredictably. You couldn't approach it. Any attempt to get close would fail. You'd be pushed away by the outflowing matter and radiation, or more accurately, there would be no geodesic path that takes you inside. The geometry of spacetime forbids entry. Theoretically beautiful, practically problematic. We've never observed anything resembling a white hole. No astronomical object emits matter and light while preventing anything from entering. If white holes existed, they'd be obvious, bright, violent, unlike anything else in the universe. We'd have seen them by now. There's also the question of how they'd form. Black holes form from collapsing stars. The formation process is well understood. Gravity overwhelms other forces. Matter collapses. An event horizon forms. But white holes? No known process creates them. You can't collapse matter into a white hole. The white hole's geometry prevents matter from entering. Some physicists speculate white holes might have formed in the early universe, when spacetime was highly curved and chaotic. Perhaps quantum fluctuations or other exotic processes created white holes shortly after the Big Bang, but they'd be unstable. The slightest perturbation would destroy them or convert them into black holes. Another possibility is that white holes are black holes viewed backward in time. A black hole's time evolution reversed would look like a white hole. Matter and radiation emerge from a singularity, pass through a horizon, and disperse into space. But this is a mathematical construct, not a physical object existing in our universe's future. The connection between black holes and white holes through a wormhole is also problematic. The wormhole in the Schwarzschild solution isn't traversable. It pinches off too quickly. Matter falling into the black hole can't reach the white hole. The geometry doesn't allow it. The connection exists mathematically, but not in any practical sense. White holes might also violate the second law of thermodynamics. They'd represent a decrease in entropy, order emerging from chaos. The universe's entropy always increases. White holes spontaneously organizing matter and energy seems to contradict this, unless they were formed with enormous entropy in the early universe and have been decreasing the universe's total entropy ever since, which seems unlikely. Some speculative theories propose that the Big Bang itself was a white hole, a singularity that expelled all the matter and energy in the universe. This is intriguing but not widely accepted. The Big Bang involved the expansion of space-time itself, not matter emerging from a fixed point in pre-existing space. Different geometry. White holes remain theoretical. They're solutions to Einstein's equations, mathematically valid, but we've never seen one. We don't know how they'd form. They might be impossible for reasons we don't fully understand. Perhaps quantum gravity forbids them. Perhaps they exist only as mathematical curiosities, not physical objects. They're the black hole's mirror image. Fascinating to think about, but almost certainly not real, at least not in the universe we observe. Gravity dominates the universe. It holds you to the ground. It keeps planets in orbit. It binds galaxies together. It shapes the cosmos. You'd think it must be incredibly strong. It's not. Gravity is by far the weakest of the four fundamental forces. Absurdly weak, laughably weak. A small fridge magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire Earth. One tiny magnet versus a planet with a mass of 6 times 10 circumflex 24 kilograms. The magnet wins easily. The four fundamental forces are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Electromagnetism holds atoms together, creates chemical bonds, generates light. The weak force governs radioactive decay. The strong force binds quarks into protons and neutrons, holds atomic nuclei together. Compare their strengths. If you set the strong force to 1, the electromagnetic force is about 137th. The weak force is about 10 circumflex 6. And gravity? About 10 circumflex 39. That's a decimal point followed by 38 zeros, then a 1. Gravity is 39 orders of magnitude weaker than electromagnetism. Why don't we notice? Because electromagnetism cancels out on large scales. Most matter is electrically neutral. Atoms have equal numbers of protons and electrons. Positive and negative charges balance. You can stand next to another person and feel no electromagnetic force, because both of you are neutral overall. But gravity doesn't cancel. There's only one type of gravitational charge, which is mass and energy. Everything with mass attracts everything else. No repulsion, no cancellation. So even though gravity is incredibly weak, it adds up over large scales. Trillions of atoms, all pulling in the same direction. That's why gravity dominates at planetary, stellar, and galactic scales. Not because it's strong, but because it accumulates. Electromagnetic forces between different parts of a planet mostly cancel. Gravitational forces don't. They add up. The more mass you have, the stronger the total gravitational effect. On small scales, gravity is negligible. Two people standing a meter apart attract each other gravitationally, but the force is less than the weight of a single bacterium. You'd never notice it. The electromagnetic forces from air molecules buffeting you completely swamp such a tiny effect. Detecting gravitational attraction between human-scale objects requires extraordinary precision. The Cavendish experiment in 1798 measured the gravitational force between lead spheres using a delicate torsion balance. The spheres had to be massive, the apparatus incredibly sensitive, and the room isolated from vibrations and air currents. Even then, the effect was barely measurable. Modern gravitational wave detectors like LIGO measure changes in distance smaller than a proton's diameter. They need 4-kilometer arms and incredibly sophisticated isolation from noise. And they're not measuring local gravity. They're measuring ripples in space-time from black hole collisions billions of light-years away. That's how weak gravity is. We need cosmic catastrophes to produce signals we can detect. Why is gravity so weak? Nobody knows. This is called the hierarchy problem. The other forces are roughly similar in strength, within a few orders of magnitude. Gravity is 39 orders of magnitude weaker. That's a huge gap. There's no obvious reason for it. Some theories propose extra dimensions. Maybe gravity spreads out into dimensions we can't access, diluting its strength in our three-dimensional space. Other forces are confined to our dimensions, so they remain strong. Interesting idea, but unproven. Other theories suggest gravity might get stronger at very short distances, possibly becoming as strong as the other forces at the Planck scale, about 10 circumflex 35 meters. We can't test this directly, because we can't probe such small distances with current technology. The weakness of gravity is both strange and fortunate. If gravity were as strong as electromagnetism, the universe would be very different. Stars would form easily but burn out quickly. Black holes would form from much smaller masses. Planets might not exist. Life, if it existed at all, would be unrecognizable. Gravity is weak. A fridge magnet proves it. Yet gravity shapes the universe because it never cancels, only accumulates. Strange that the weakest force dominates the cosmos. In physics, we expect things to be roughly the same order of magnitude, unless there's a good reason for them to be different. The electromagnetic force and the weak nuclear force differ by a factor of about 10 circumflex 32. That's huge, but we understand why. The weak force is mediated by very massive particles, W and Z bosons. Their mass suppresses the force's strength at low energies. We have an explanation. Gravity and electromagnetism differ by a factor of 10, circumflex 39. That's not just huge, it's incomprehensibly huge. And we don't have a good explanation. This is the hierarchy problem. Why is gravity so extraordinarily weak compared to the other forces? In quantum field theory, virtual particles contribute to force strengths. These contributions should drive forces to similar values, unless something prevents it. For gravity, there's no known mechanism suppressing its strength. It should be much stronger than it is. Yet, it's not. Why? One possibility is that we're missing something fundamental about how gravity works. Maybe gravity isn't a force at all in the same sense as the others. We know it's the curvature of space-time, not an exchange of particles. But at the quantum level, we expect gravitons, hypothetical particles that mediate gravitational interactions. If they exist, why don't they make gravity stronger? Another approach involves extra dimensions. Our universe might have more than 3 spatial dimensions. The extra dimensions could be compactified, curled up so small we don't notice them. Normal forces like electromagnetism would be confined to our three dimensions, but gravity could spread out into all dimensions. This would dilute gravity's strength in our three-dimensional space. Imagine turning a garden hose on a wall. The water hits the wall in a concentrated stream, but if you poke holes in the hose along its length, water sprays out in all directions. Less water hits the wall. Similarly, if gravity leaks into extra dimensions, less of it affects our three-dimensional space. The force appears weak. This idea is testable in principle. If extra dimensions exist and gravity leaks into them, gravity might deviate from Newton's inverse square law at very small distances. Instead of falling off as 1r, it might fall off faster. Experiments have looked for this. So far, no deviations detected. Either the extra dimensions are smaller than we can probe, or they don't exist. String theory offers another perspective. In string theory, all particles are vibrations of tiny strings. Different vibration patterns correspond to different particles. The graviton is one such pattern. String theory predicts gravity's strength based on the properties of these strings, but the calculations involve the Planck mass, which is enormous compared to particle masses we normally deal with. This might explain why gravity is weak, but the explanation isn't fully satisfactory. It pushes the question back. Why is the Planck mass so large? Some physicists propose that the hierarchy is an environmental selection effect. Maybe many universes exist with different force strengths. We find ourselves in one where gravity is weak because that's necessary for life. If gravity was stronger, stars would burn out too quickly for life to evolve. Planets might not form stably. Only universes with weak gravity develop observers to notice the hierarchy. Anthropic reasoning. Not everyone finds this satisfying. Another idea involves supersymmetry. This theory proposes that every particle has a heavier superpartner. These superpartners would cancel certain quantum corrections that could make gravity stronger. But we haven't detected any superpartners despite extensive searches at particle accelerators. If supersymmetry exists, it's broken at high energies, and we don't fully understand how or why. The hierarchy problem remains unsolved. We don't know why gravity is 10 circumflex, 39 times weaker than electromagnetism. It's one of the deepest mysteries in fundamental physics. The answer might require new physics beyond our current theories. Extra dimensions, supersymmetry, something we haven't thought of yet. Until we solve it, the hierarchy problem reminds us how much we don't understand. Gravity dominates the universe at large scales, but at the fundamental level, it's bizarrely, inexplicably weak, and we don't know why. Physics rests on two pillars. General relativity describes gravity, spacetime, and the cosmos. Quantum mechanics describes atoms, particles, and the microscopic world. Both theories are spectacularly successful in their domains, and they're fundamentally incompatible. General relativity is deterministic. If you know the curvature of spacetime and the initial conditions, you can calculate the past and future with certainty. No randomness, no uncertainty. Spacetime is smooth, continuous, classical. Particles follow definite trajectories called geodesics. Quantum mechanics is probabilistic. Particles don't have definite positions or velocities until measured. They exist in superpositions, combinations of multiple states, simultaneously. Measuring a particle collapses the superposition, giving one outcome randomly according to probabilities. The future is uncertain, determined only statistically. These are opposite worldviews. One deterministic, one probabilistic. One smooth, one grainy. One based on geometry, one based on wave functions. For most situations, we can ignore the conflict. Use quantum mechanics for atoms and molecules. Use general relativity for planets and stars. The domains don't overlap, but sometimes they do. Inside black holes, space-time curvature becomes extreme at tiny scales. Both quantum effects and gravitational effects are important. At the Big Bang, the entire universe was smaller than an atom. Quantum mechanics and gravity both mattered. We need a theory that combines them. Quantum gravity. The problem is that when you try to apply quantum mechanics to gravity, you get nonsense. Infinities appear in the calculations. The math breaks down. This doesn't happen with other forces. Electromagnetism, the weak force, the strong force, all have successful quantum theories. Quantum electrodynamics describes light and electrons with incredible precision. Quantum chromodynamics describes quarks and the strong force. These theories work beautifully, but quantum gravity doesn't work. When you try to quantize general relativity using the same techniques, the equations give infinite answers. This usually means the theory is incomplete, missing something important. Part of the problem is that gravity is space-time curvature. In quantum mechanics, you quantize fields that exist in space-time. But with gravity, you're trying to quantize space-time itself. The arena becomes part of the show. The background becomes dynamic. This leads to conceptual and mathematical difficulties we don't face with other forces. Another issue is scale. Quantum effects dominate at small scales. Gravitational effects dominate at large scales. The overlap occurs at the Planck scale, about 10 circumflex 35 meters and 10 circumflex 43 seconds. That's 20 orders of magnitude smaller than a proton. We have no way to probe that scale directly. No particle accelerator can reach the energies required. No experiment can test theories of quantum gravity directly. So we're stuck theorizing without experimental guidance. Different approaches compete. String theory, loop quantum gravity, causal sets, asymptotic safety. Each tries to merge quantum mechanics and gravity in different ways. None are confirmed. None make predictions we can test with current technology. The incompatibility matters for fundamental questions. What happens at the center of a black hole? General relativity predicts a singularity, infinite curvature. But surely quantum effects prevent true infinities. What does quantum mechanics say? We don't know, because we don't have quantum gravity. What happened at the Big Bang? The universe was smaller than an atom, denser than anything imaginable. Classical general relativity breaks down. Quantum effects must have been crucial. But which quantum effects? What was the quantum state of the universe? We can't answer without quantum gravity. Is space-time fundamental or emergent? Does it break down into discrete chunks at the Planck scale? Or is it smooth all the way down? Does time itself become meaningless at small enough scales? These questions require quantum gravity to answer. The two pillars of physics don't connect. They're both correct in their domains, but they rest on incompatible foundations. One will have to give. Either quantum mechanics needs modification at extreme scales, or general relativity does, or both do. We'll need a deeper theory that encompasses both as special cases. Quantum mechanics hates gravity, or maybe gravity hates quantum mechanics. Either way, they don't get along. And until we reconcile them, our understanding of the universe remains fundamentally incomplete. String theory is one of the leading candidates for a theory of quantum gravity. The basic idea is radical. Particles aren't point-like. They're tiny, vibrating strings, unimaginably small, about 10 circumflex, 35 meters long. Different vibration patterns correspond to different particles. An electron is a string vibrating one way. A quark is the same string vibrating differently. A photon is another vibration pattern. And crucially, the graviton, the hypothetical particle that carries gravity, emerges naturally as one of the string's possible vibrations. Gravity isn't added to the theory. It arises automatically from the mathematics of vibrating strings. This is string theory's great achievement. When you quantize strings, gravitons appear in the equations without being put in by hand. General relativity emerges from string theory in the appropriate limit. The theory unifies gravity with the other forces because all forces come from the same fundamental objects, vibrating strings. But the theory comes with strange requirements. It only works consistently in 10 or 11 dimensions. Not the 3 spatial dimensions and 1 time dimension we experience. 10 or 11 total dimensions. Where are the extra dimensions? The standard explanation is that they're compactified, curled up so small we don't notice them. Imagine an ant walking on a wire. From far away, the wire looks one-dimensional. The ant can only move forward or backward. But zoom in, and the wire has thickness. It's actually a thin cylinder. The ant could also walk around the wire's circumference. That's a second dimension, but it's curled up, forming a tiny circle. Similarly, our universe might have extra dimensions curled up into tiny shapes at every point in space, so small that even atoms don't notice them. Only at the string scale, 10 circumflex 35 meters, with the extra dimensions become apparent. We can't probe that scale experimentally, so we don't see the extra dimensions directly. The shape of these compactified dimensions determines the properties of particles we observe. Different shapes give different physics. This is simultaneously string theory's strength and weakness. It's flexible enough to accommodate the particles and forces we see, but that flexibility means it doesn't make unique predictions. There are roughly 10 circumflex, 500 possible ways to compactify the extra dimensions. Each gives a different universe with different physical laws. String theorists have worked on the mathematics for decades. They've discovered remarkable connections between different areas of physics and mathematics. Dualities that show apparently different string theories are actually equivalent. Insights into black hole thermodynamics, tools that have been useful in other areas of physics. But they haven't made a testable prediction that distinguishes string theory from other approaches. The theory might be correct, but we can't verify it experimentally with current technology. Critics argue it's not even science if it can't be tested. Proponents argue it's the only mathematically consistent theory of quantum gravity we have. One prediction involves extra particles called superpartners. String theory requires supersymmetry, a symmetry between bosons and fermions. Every particle should have a heavier superpartner. The Large Hadron Collider has searched extensively for these particles. None found. Either they're heavier than the LHC can produce, or supersymmetry is broken in a way we don't understand, or string theory is wrong. String theory also predicts that the fundamental constants of nature, things like the strength of gravity or the mass of the electron, depend on the shape of the compactified dimensions. In principle, different regions of space could have different shapes, meaning different physics. This leads to the string theory landscape, a vast collection of possible universes. Our universe is just one. Some theorists find this appealing. It explains why our universe's constants seem fine-tuned for life. There are 10 circumflex 500 universes with different constants. We exist in one where the constants allow life because that's the only type where observers can exist. Selection effect. Others find it unsatisfying. Science usually seeks unique, testable predictions. The landscape gives too many possibilities. If anything can happen, the theory explains nothing. String theory is mathematically beautiful. It unifies gravity with other forces. It requires extra dimensions and predicts a rich structure of particles and interactions. But after decades of work, it remains unconfirmed. We don't know if strings are real or mathematical fiction. It's an attempt at reconciliation. Quantum mechanics and gravity brought together through vibrating strings in 11 dimensions. Elegant, unproven, and possibly untestable with foreseeable technology. String theory isn't the only approach to quantum gravity. Loop quantum gravity takes a different path. Instead of adding extra dimensions or new objects like strings, it directly quantizes spacetime itself. Space becomes grainy, made of discrete chunks. The idea is that spacetime, at the smallest scales, isn't smooth. It's a network of loops and nodes. Think of spacetime like a fabric woven from threads. From a distance, it looks continuous. Zoom in, and you see the individual threads and the spaces between them. Loop quantum gravity says spacetime has this discrete structure at the Planck scale, about 10 circumflex 35 meters. Space is quantized. There's a minimum volume, roughly 10 circumflex, 105 cubic meters. You can't divide space into anything smaller. Similarly, there's a minimum area, about 10 circumflex 70 square meters. These are unimaginably tiny, but they're finite. Space comes in discrete chunks, not continuous. Time might also be discrete. There could be a minimum interval of time, the Planck time, about 10 circumflex 43 seconds. Time doesn't flow smoothly. It ticks forward in discrete steps like frames in a movie. Smooth motion is an illusion arising from many tiny discrete jumps. This solves some of general relativity's problems. In classical general relativity, black hole singularities and the Big Bang singularity have infinite density and curvature. The math breaks down. But if space is made of discrete chunks, density can't be infinite. There's a maximum density, set by the Planck scale. The singularities smooth out into regions of high but finite density. Loop quantum gravity also avoids the infinities that plague attempts to quantize general relativity, using standard techniques. Because spacetime is discrete, certain calculations that gave infinite answers in the classical theory give finite answers. The theory is mathematically well defined, at least in simplified versions. Unlike string theory, loop quantum gravity doesn't require extra dimensions. It works in the familiar 3 spatial dimensions plus time. It doesn't predict a zoo of new particles or forces. It's conservative in that sense. It takes general relativity and quantum mechanics as given and tries to combine them directly. But loop quantum gravity has problems too. It's incomplete. The theory works well for describing spacetime's quantum structure in simplified scenarios. But extracting predictions for real-world physics is difficult. How does smooth spacetime emerge from the grainy structure at larger scales? How do particles and fields behave on this discrete background? These questions don't have complete answers yet. Loop quantum gravity doesn't automatically include the other forces. It's a theory of quantum gravity alone. You have to add the electromagnetic weak and strong forces separately. This is the opposite of string theory, which unifies all forces but requires exotic new structures. Loop quantum gravity is minimal but doesn't unify. One intriguing prediction is that light of different colors might travel at slightly different speeds when passing through quantum spacetime. High-energy photons would interact differently with the discrete structure than low-energy photons. Over cosmic distances, this could cause observable effects. Photons from distant gamma-ray bursts might arrive at slightly different times, depending on their energy. Observations have looked for this. So far, no effect detected. Either quantum spacetime doesn't affect light propagation this way, or the effect is smaller than we can currently measure. It's a testable prediction, which is valuable. But so far, the tests haven't confirmed loop quantum gravity. Another prediction involves black hole thermodynamics. Loop quantum gravity calculates the entropy of black holes from first principles by counting quantum states of the horizon. The result matches the Bekenstein-Hawking formula derived from classical and semi-classical arguments. This is encouraging. The theory reproduces a known result from a completely different starting point. Cosmology is another area where loop quantum gravity makes predictions. The Big Bang singularity might be replaced by a big bounce. Instead of the universe emerging from infinite density, it might have bounced from a previous contracting phase. The contraction stopped at Planck density, then reversed into expansion. No singularity. No moment of infinite curvature. This is speculative but testable in principle. A bounce might leave signatures in the cosmic microwave background, patterns in the ancient radiation that differ from standard Big Bang predictions. Astronomers are looking for these signatures. None found yet, but the searches continue. Loop quantum gravity is an alternative. It quantizes spacetime directly, making space discrete at the smallest scales. It avoids some of general relativity's infinities. It's simpler than string theory in some ways, more complicated in others. And like string theory, it remains unconfirmed. The quest for quantum gravity has two main paths: strings and loops. Both are works in progress. Both might be wrong, or one might be right, or they might both be aspects of a deeper theory we haven't discovered yet. Time and experiment will tell. Every force in the standard model of particle physics is mediated by particles. Photons carry the electromagnetic force. W and Z bosons carry the weak nuclear force. Gluons carry the strong nuclear force. These are force carriers, particles exchanged between other particles to create forces. If gravity is a force in the same sense, it should also have a force carrier, the graviton, a massless particle with spin 2 traveling at the speed of light. Two particles with mass would exchange gravitons, and this exchange would create the gravitational attraction between them. This is how quantum field theory describes forces. Forces arise from particle exchanges. The electromagnetic force between two electrons comes from exchanging virtual photons. These photons pop into existence briefly, get exchanged, and vanish. The particles don't travel from one electron to the other in the classical sense. They're quantum fluctuations mediating the interaction. Gravitons would work similarly. Two masses exchange virtual gravitons. This creates the gravitational force between them. The more massive the objects, the more gravitons exchanged, the stronger the force. Gravity would be quantized just like electromagnetism. There's a problem. We've never detected a graviton. Not one. And we likely never will. Gravitons would interact incredibly weakly with matter, far weaker than neutrinos, which are already notoriously difficult to detect. Building a detector sensitive enough to catch a single graviton seems impossible with any foreseeable technology. Consider what it would take. A graviton detector would need to be enormous, potentially the mass of Jupiter, to have enough matter for a reasonable chance of interaction. And it would need to be isolated from all other disturbances. Vibrations, thermal noise, cosmic rays, everything would swamp the tiny signal from a single graviton. The detector would need to be more sensitive than anything we can build by many orders of magnitude. So we can't detect gravitons directly, but we can infer their properties from theory. If gravity is quantized, gravitons must exist. They'd be massless because gravity has infinite range. Massive force carriers like W and Z bosons give forces finite range. Gravity's range is infinite, so gravitons must be massless. Gravitons would have spin 2. This is required by the mathematics of general relativity. Forces mediated by spin 1 particles behave differently than gravity. Only spin 2 particles produce a force with gravity's properties, always attractive, coupling to all forms of energy and momentum, producing space-time curvature. String theory predicts gravitons naturally. One of the string's vibration patterns has the properties of a graviton. This is considered strong evidence for string theory. The theory didn't need to be designed to include gravity. Gravitons emerged automatically from the mathematics. Loop quantum gravity doesn't describe gravitons in the same way. It quantizes space-time directly rather than treating gravity as particle exchanges. But gravitons might emerge as excitations of the quantized geometry, ripples in the network of loops and nodes. The connection isn't as clear as in string theory. Gravitational waves are sometimes described as consisting of gravitons. Just as light waves are made of photons, gravitational waves would be made of gravitons. LIGO detects gravitational waves, so in a sense, it's detecting huge numbers of gravitons collectively, but it's not resolving individual gravitons. The wave is a classical phenomenon, the collective behavior of countless gravitons. This is similar to how we usually experience light. You see light as waves, not individual photons. Only in carefully controlled experiments with very weak light do you detect single photons. Similarly, we experience gravity as a classical field, not individual graviton exchanges. Only in theoretical calculations do gravitons appear explicitly. The existence of gravitons is almost certain if quantum mechanics applies to gravity. Every other force has quantum carriers. Gravity should too, but detecting them individually is probably impossible. They'll remain theoretical constructs, inferred from theory rather than observed directly. Gravitons are the particles that would carry gravity if gravity is a quantum force. They're predicted by multiple theoretical frameworks. They're consistent with everything we know. But they're hypothetical. We've never caught one, and we almost certainly never will. Galaxies rotate. Stars orbit the galactic center, held in place by gravity. In the 1970s, astronomer Vera Rubin measured how fast stars at different distances from galactic centers were moving. The results didn't make sense. Based on visible matter, stars in the outer regions should orbit slowly. Most of a galaxy's visible mass is concentrated in the center. Stars far from the center should feel weak gravity and orbit slowly, just like planets far from the sun orbit more slowly than planets close in. But that's not what Rubin observed. Stars in the outer regions were moving just as fast as stars closer in. Some galaxies had flat rotation curves, velocity barely decreasing with distance. The gravity holding these stars in orbit was much stronger than the visible matter could account for. Either Newton's and Einstein's theories of gravity were wrong, or there was additional mass we couldn't see. Dark matter. Matter that doesn't emit, absorb, or reflect light. Invisible to telescopes. But it has mass, so it curves spacetime and affects visible matter through gravity. The evidence has mounted over decades. Galaxy clusters show the same problem. The visible mass isn't enough to hold them together. The galaxies are moving too fast. Without additional mass, the clusters should fly apart. But they don't. Gravitational lensing provides more evidence. Galaxy clusters bend light from background galaxies. By measuring how much bending occurs, we can calculate the cluster's total mass. The answer is always much more than the visible matter. Most of the mass is dark. In some cases, dark matter has been mapped directly using gravitational lensing. The bullet cluster is a famous example. Two galaxy clusters collided and passed through each other. The hot gas in the clusters interacted and slowed down, staying in the collision region, but the dark matter passed through without interacting, continuing with the galaxies. Gravitational lensing shows where the mass is. Most of it is with the galaxies, not with the gas. The dark matter is visible through its gravitational effects, separated from the ordinary matter. Direct evidence that dark matter exists and doesn't interact electromagnetically. The cosmic microwave background provides additional confirmation. Tiny temperature fluctuations in this ancient radiation encode information about the universe's composition when it was only 380,000 years old. The pattern of fluctuations matches predictions if the universe contains about 85% dark matter and 15% ordinary matter by mass. So what is dark matter? We don't know. It's not ordinary matter like protons, neutrons, and electrons. That's called baryonic matter. Dark matter must be something else. Leading candidates are exotic particles that don't interact via electromagnetism or the strong force. They'd only interact via gravity, and possibly the weak force. One candidate is WIMPs, weakly interacting massive particles. These would be particles with mass similar to atoms, but only interacting through gravity and the weak force. Scientists have built sensitive detectors deep underground to catch WIMPs colliding with ordinary atoms. So far, no confirmed detections. Another candidate is axions, much lighter hypothetical particles. They'd be produced in enormous numbers and interact incredibly weakly. Experiments are searching for them too. No confirmed detections yet. Primordial black holes are another possibility. Tiny black holes formed in the early universe could constitute dark matter. They'd have mass, but no light. However, various observations constrain how many primordial black holes can exist. They probably don't account for all dark matter, though they might contribute. Some physicists propose modifying gravity instead. Maybe Newton's and Einstein's theories don't work on galactic scales. Modified Newtonian dynamics, MOND, is one such approach. It modifies gravity to be stronger in weak fields, explaining galaxy rotation without dark matter. But MOND struggles to explain galaxy clusters and gravitational lensing observations. It doesn't match the cosmic microwave background data. Most physicists think dark matter is more likely than modified gravity. Dark matter is a mystery. We see its effects everywhere. It outweighs ordinary matter 5 to 1. It shaped the universe's structure, providing gravitational wells for galaxies to form. Without it, galaxies as we know them wouldn't exist. Neither would we. But we don't know what it's made of. Decades of searching have yielded no direct detection. It reveals itself only through gravity, and gravity, the weakest force, is the only way we know it's there. When you observe a spiral galaxy edge-on, you can measure how fast stars at different distances from the center are moving. This creates a rotation curve, a graph of orbital velocity versus distance from the galactic center. Based on Newtonian gravity and the visible matter in the galaxy, you'd expect the rotation curve to rise near the center where most visible mass is concentrated, then fall off at larger distances. Just like planets in the solar system, Mercury orbits faster than Earth. Earth orbits faster than Jupiter. The farther from the Sun, the slower the orbit. But galaxies don't behave this way. The rotation curve rises as expected near the center. Then it flattens. Stars in the outer regions orbit at roughly the same speed as stars closer in. Some rotation curves stay flat out to enormous distances, far beyond where most visible stars exist. This was discovered in the 1970s by Vera Rubin and Kent Ford. They measured rotation curves for many spiral galaxies. Almost all showed the same pattern. Flat rotation curves. Stars moving too fast based on visible mass. The implication is clear. There's more mass than we can see. A lot more. The mass distribution extends far beyond the visible galaxy, forming a dark matter halo. This halo is roughly spherical, much larger than the visible disk. It contains several times as much mass as all the stars and gas combined. The dark matter halo's gravity is what keeps the outer stars moving fast. Without it, they'd drift away. The galaxy would gradually lose stars from its outer regions, but the dark matter provides extra gravitational pull, holding everything together. Different galaxies have different amounts of dark matter, but all massive galaxies seem to have substantial dark matter halos. Dwarf galaxies also show evidence for dark matter, though the details are more complex. The ratio of dark matter to ordinary matter varies, but dark matter always dominates. Some galaxies recently discovered appear to have little or no dark matter. These are rare and puzzling. If dark matter exists, why don't these galaxies have it? Possible explanations include that the dark matter was stripped away by interactions with other galaxies, or that these galaxies formed in unusual ways. They're still under study. Rotation curves can't be explained by modifying gravity at large distances without introducing problems elsewhere. MOND, modified Newtonian dynamics, adjusts how gravity works in weak fields. It can fit rotation curves reasonably well, but it struggles with other observations. Galaxy clusters, gravitational lensing, the cosmic microwave background. MOND doesn't match these as well as dark matter does. The standard explanation is dark matter. Each galaxy sits in a halo of it. The halo's gravity keeps stars in the outer regions moving fast. The halo is roughly spherical and extends well beyond the visible galaxy. This matches simulations of galaxy formation. When you include dark matter in the simulations, you get galaxies that look like the ones we observe. Measuring rotation curves requires spectroscopy. You observe light from stars or gas at different distances from the galactic center. The light is Doppler shifted, redder if moving away, bluer if moving toward us. From these shifts, you calculate velocities. Plot velocity versus distance, and you get the rotation curve. For nearby galaxies, this is straightforward. For distant galaxies, it's harder because individual stars aren't resolvable. But you can measure the rotation of gas using emission lines. Hydrogen gas emits light at specific wavelengths. Measure those wavelengths at different positions in the galaxy, and you map the rotation. The same pattern appears everywhere. Flat rotation curves, too much gravity for the visible matter. Dark matter halos holding galaxies together. We see this in spiral galaxies, in dwarf galaxies, in elliptical galaxies, though the analysis is more complex there. Galaxy rotation curves were one of the first strong pieces of evidence for dark matter. Combined with galaxy cluster observations and gravitational lensing, they paint a consistent picture. The universe is dominated by matter we can't see, matter that reveals itself only through gravity, and that invisible matter is what keeps galaxies from flying apart. Science advances when observations don't match predictions. Anomalies are opportunities. They point to gaps in our understanding. Sometimes they're measurement errors. Sometimes they're new physics. Gravitational anomalies fall into this category. Observations where gravity seems to behave differently than expected. Most have been explained. Some remain mysterious. The perihelion precession of Mercury was an anomaly for decades. Mercury's orbit is an ellipse that slowly rotates. This precession can be calculated using Newtonian gravity, accounting for the gravitational pull of other planets. But the observed precession was 43 arcseconds per century more than predicted. Tiny, but measurable. No one knew why. Einstein's general relativity explained it immediately. The extra precession comes from spacetime curvature near the Sun. In general relativity, orbits in curved spacetime precess slightly more than Newtonian predictions. The amount matched observations perfectly. Anomaly solved. The Pioneer anomaly was more recent. Pioneer 10 and 11, spacecraft launched in the 1970s, showed a small, unexplained deceleration as they left the solar system. They were slowing down more than predicted based on the Sun's gravity and known forces. The effect was tiny, about 10 circumflex, 10 meters per second squared, but it was consistent over decades. Some speculated it might be new physics. Maybe gravity behaves differently at large distances. Maybe dark matter in the solar system was causing drag. Exotic explanations abounded. But, after careful analysis, the anomaly was explained by thermal radiation. The spacecraft emit heat unevenly. This creates a small thrust, like a rocket, in the opposite direction. The anomaly wasn't gravitational. It was thermodynamics. The flyby anomaly is still unresolved. Spacecraft performing gravity assist maneuvers around Earth sometimes show tiny velocity changes that don't match predictions. The discrepancies are small, millimeters per second, but they're real. Multiple spacecraft have shown it. Possible explanations include thermal effects, atmospheric drag at high altitudes, tidal effects, or uncertainty in Earth's gravitational field. None fully explain all the observations. It might be a combination of mundane effects we haven't modeled precisely, or it might be something new. Still under investigation, dark energy itself is a gravitational anomaly. The universe's expansion is accelerating. Based on the matter content, gravity should be slowing the expansion. Instead, something is pushing space apart. We call it dark energy, but we don't know what it is. It might be a cosmological constant, energy inherent to empty space, or it might be a dynamic field changing over time. Observations are trying to distinguish between these. Another anomaly involves the Hubble constant, the rate of the universe's expansion. Different measurement methods give slightly different values. Measurements using the cosmic microwave background give one value. Measurements using supernovae and Cepheid variables give another. The discrepancy is small, but statistically significant. It's called the Hubble tension. This might be a measurement error, or it might indicate new physics. Maybe the universe's expansion history is more complicated than our models assume. Maybe dark energy evolves over time. Maybe there's some other effect we haven't accounted for. Resolving this anomaly is a major goal in cosmology. Some galaxies show rotation curves that don't quite match dark matter predictions. The distribution of dark matter inferred from rotation curves doesn't always match what simulations predict. This is called the core cusp problem. Simulations tend to produce dark matter halos with cusps, dense centers. Observations suggest some galaxies have cores, flatter central regions. This might mean our dark matter simulations are missing physics. Feedback from star formation and supernovae can redistribute matter, flattening cusps into cores. Or it might mean dark matter has properties we haven't accounted for. Self-interacting dark matter, for instance, might behave differently than the simplest models assume. Gravitational anomalies are clues. Sometimes they point to mistakes in our models or measurements. Sometimes they point to new physics. Mercury's precession led to general relativity. The accelerating expansion led to dark energy. We don't know what current anomalies will lead to. That's what makes them exciting. What if there's no dark matter? What if instead gravity just works differently than we think at large scales? This is the premise of modified Newtonian dynamics, MOND for short, proposed by physicist Mordechai Milgram in 1983. MOND offers a radical alternative to dark matter. Instead of adding invisible matter to explain galaxy rotation curves, it modifies how gravity behaves in weak gravitational fields, the kind of fields that exist at the edges of galaxies. The idea is simple. Newton's second law says force equals mass times acceleration, F equals ma. This works perfectly in strong gravitational fields like Earth's surface or the inner solar system. But MOND proposes that in extremely weak fields, below a certain acceleration threshold about 10 circumflex 10 meters per second squared, gravity behaves differently. The relationship between force and acceleration changes. In these weak fields, the effective gravitational force becomes stronger than Newtonian gravity predicts. This extra strength explains why stars at the edges of galaxies orbit faster than expected. You don't need dark matter. You just need gravity to work differently in weak fields. And it works. MOND fits galaxy rotation curves remarkably well. With a single parameter, the acceleration threshold, you can explain the rotation curves of hundreds of galaxies. No need to invoke massive dark matter halos. The fit is often better than dark matter models, because dark matter requires assumptions about how the dark matter is distributed. MOND also makes a striking prediction called the Tully-Fisher relation. This is an observed correlation between a galaxy's total luminosity and its rotation velocity. Brighter galaxies rotate faster. MOND explains this naturally. Dark matter models can reproduce it, but require fine-tuning. So why doesn't everyone accept MOND? Because it has serious problems beyond galaxy rotation curves. Galaxy clusters are the first major issue. Clusters contain hundreds or thousands of galaxies bound together by gravity. When you apply MOND to clusters, it doesn't provide enough gravitational force to hold them together. Even with modified gravity, you still need additional matter beyond what's visible. MOND reduces the amount of missing mass, but doesn't eliminate it. You still need some dark matter, which defeats the purpose. Gravitational lensing is another problem. MOND doesn't naturally explain how light bends around massive objects. General relativity predicts light bending based on spacetime curvature. MOND is a modification of Newtonian gravity, not general relativity. To explain lensing, you need a relativistic version of MOND. Several have been proposed, TeVes being the most developed, but they're complicated and not as elegant as MOND itself. The cosmic microwave background is perhaps MOND's biggest challenge. The pattern of temperature fluctuations in this ancient radiation encodes information about the universe's composition at 380,000 years old. The pattern matches predictions beautifully if the universe contains about 85% dark matter and 15% ordinary matter. MOND struggles to reproduce this pattern. The physics of the early universe involves strong gravitational fields, where MOND reduces to ordinary gravity. So MOND doesn't help explain the cosmic microwave background. You need dark matter, or at least something behaving like dark matter, in the early universe. The bullet cluster is another killer observation for MOND. Two galaxy clusters collided and passed through each other. The hot gas stayed in the collision region. The galaxies and dark matter, detected through gravitational lensing, passed through with minimal interaction. This spatial separation between ordinary matter and gravitational mass is hard to explain with modified gravity. It's natural with dark matter. MOND also lacks a theoretical foundation. It's an empirical formula that fits observations but doesn't come from deeper principles. Why would gravity change behavior at a specific acceleration scale? What's special about 10 circumflex 10 meters per second squared? Dark matter, for all its mysteries, fits into our understanding of particle physics and cosmology. MOND doesn't have that theoretical grounding. Some physicists continue working on MOND and its relativistic extensions. They've had some successes. MOND correctly predicted that low surface brightness galaxies, which are very dim and diffuse, would show strong rotation curve anomalies. This was confirmed observationally after the prediction. But the accumulation of evidence favors dark matter. MOND works well for spiral galaxies. That's its strength. But the universe includes galaxy clusters, gravitational lensing, the cosmic microwave background, and the bullet cluster. Dark matter explains all of these with one hypothesis. MOND struggles with most of them. It's possible both ideas have merit. Maybe gravity is modified at certain scales, and there's some dark matter. Maybe MOND is an approximation of some deeper theory. Or maybe MOND is just wrong, a clever idea that doesn't match reality. The debate continues. MOND challenges us to question assumptions. Maybe dark matter exists. Maybe gravity is stranger than we think. Or maybe both are partly true. We won't know until we detect dark matter directly or find compelling evidence that gravity really does behave differently at galactic scales. Dark matter was strange enough. Invisible matter that only interacts through gravity, making up 85% of all matter. But at least it behaves like matter. It clumps together. It helps galaxies form. It attracts things gravitationally. Dark energy is stranger. It doesn't clump. It doesn't attract. It pushes. It's spread uniformly throughout space, and it's causing the universe's expansion to accelerate. Space itself is being pushed apart, and we have no idea why. The evidence comes from observations of distant supernovae. Type 1A supernovae are remarkably consistent in brightness. They're standard candles. Astronomers can use them to measure distances across billions of light years. In the late 1990s, two teams independently used this technique to map the universe's expansion history. They expected to find that expansion was slowing down. After the Big Bang, the universe started expanding. Gravity should gradually slow that expansion. The universe might eventually stop expanding and collapse back in a big crunch. Or it might expand forever, but at a decreasing rate. Either way, deceleration. Instead, they found acceleration. The universe's expansion is speeding up. Distant supernovae are dimmer than expected, meaning they're farther away than they should be if expansion were decelerating. Something is pushing space apart, overcoming gravity. This discovery was so unexpected that it was initially met with skepticism. The observations were repeated and confirmed. More data accumulated. By the early 2000s, the evidence was overwhelming. The universe's expansion is accelerating. The discovery won the Nobel Prize in Physics in 2011. What could cause this? Something with negative pressure. In general relativity, pressure contributes to gravity. Positive pressure, like in ordinary matter, adds to gravitational attraction. But negative pressure does the opposite. It creates gravitational repulsion. It pushes space apart. The simplest candidate is the cosmological constant. Einstein introduced this in 1917 as a modification to his field equations. He wanted a static universe, neither expanding nor contracting, but his equations predicted expansion or contraction. So he added a constant term, the cosmological constant, to balance gravity and keep the universe static. Then Edwin Hubble discovered the universe is expanding. Einstein's static universe was wrong. He reportedly called the cosmological constant his biggest blunder and removed it from his equations. The universe doesn't need it to be static because the universe isn't static. But the cosmological constant wasn't wrong. It was premature. If it exists, it represents energy inherent to empty space itself. Vacuum energy. Every cubic meter of space contains a tiny amount of energy, even when completely empty of matter and radiation. This vacuum energy has negative pressure and causes accelerating expansion. The observations suggest the cosmological constant has a value of about 10 circumflex 26 kilograms per cubic meter. Incredibly small, but not zero. And because space is vast, it adds up. Across the entire observable universe, dark energy makes up about 68% of the total energy content. Dark matter is about 27%. Ordinary matter is only about 5%. We're living in a universe dominated by something we don't understand. Dark energy outweighs everything else, and its effects will shape the universe's future. Because expansion is accelerating, distant galaxies are receding faster and faster. Eventually, they'll be moving away so fast that light from them can no longer reach us. Galaxies beyond a certain distance will cross what's called the cosmic event horizon. They'll be forever beyond our observational reach. In trillions of years, most galaxies will have crossed this horizon. Only galaxies in our local group, held together gravitationally, will remain visible. The rest of the universe will have expanded away. Future astronomers would see a much emptier universe. They'd have no way to know the universe had ever been fuller. The evidence for the Big Bang, for cosmic expansion, for the history of the cosmos, would all be gone. They'd be observationally isolated. We're fortunate to live when we can still see most of the universe, when evidence for its history is still available. This window won't last forever. Dark energy is emptying the observable universe. Is the cosmological constant the right explanation? Maybe. It fits the data. But it has a problem. Quantum field theory predicts vacuum energy should exist. When you calculate how much, you get a number 120 orders of magnitude larger than observed. This is called the cosmological constant problem, and it's one of the worst theoretical predictions in physics. More on that shortly. Alternatively, dark energy might not be constant. It might be a dynamic field that changes over time. Quintessence. One such proposal involves a scalar field that varies across space and time. This would allow dark energy's strength to change, possibly even reversing from repulsive to attractive in the far future. Observations are trying to determine whether dark energy is constant or dynamic. Measuring supernovae at different distances and redshifts maps the expansion history. So far, the data is consistent with a cosmological constant, but the uncertainties are still large enough that other models aren't ruled out. Dark energy is stranger than dark matter. It doesn't clump or attract. It fills space uniformly and pushes everything apart. It dominates the universe's energy budget, and we have no idea what it fundamentally is. Just that it's there, accelerating cosmic expansion, shaping the universe's ultimate fate. The universe is expanding. Galaxies are moving apart. Space itself is stretching. This has been known since Edwin Hubble's observations in the 1920s. But for decades, astronomers assumed the expansion was slowing down. The reasoning was straightforward. Gravity attracts. Every galaxy pulls on every other galaxy. This gravitational attraction should gradually slow the expansion, like throwing a ball upward. Gravity slows it. Eventually it might stop and fall back, or it might escape, but still decelerate. The critical question was how much matter the universe contains. Enough matter and gravity would eventually halt expansion, causing the universe to collapse in a big crunch. Too little matter and expansion would continue forever, but slowing down. The universe appeared close to the critical density. Maybe it would barely escape collapse. In the 1990s, two teams set out to measure the deceleration precisely: the Supernova Cosmology Project and the High Z Supernova Search Team. They used Type Ia supernovae as distance markers. These supernovae are remarkably consistent in brightness because they're caused by white dwarfs reaching a specific mass limit and exploding. Standard candles. By measuring how bright a supernova appears compared to how bright it actually is, you calculate its distance. By measuring its redshift, how much its light has been stretched by cosmic expansion, you calculate how fast it's receding. Combine many supernovae at different distances, and you map the expansion history of the universe. The teams expected to measure deceleration. Slower expansion in the past compared to now would mean gravity had been winning. Instead, they found the opposite. Distant supernovae were dimmer than expected. This meant they were farther away than they should be if expansion had been decelerating. The only explanation: expansion was accelerating. The announcement in 1998 shocked the physics community. Accelerating expansion violated all expectations. It meant something was overpowering gravity on cosmic scales, something repulsive, something pushing space apart. The data kept coming in. More supernova, more distances, more redshifts. The conclusion held. Expansion began decelerating in the early universe when matter dominated. But about 5 billion years ago, something changed. Dark energy, which had always been present but relatively weak, became dominant as the universe expanded and matter became more dilute. Expansion started accelerating. We're living in the era of acceleration, and it's going to continue. As the universe expands, matter becomes even more dilute. Dark energy's dominance increases. Acceleration gets stronger. The future of the universe is runaway expansion. This has profound implications. Galaxy formation requires gravity to overcome expansion and pull matter together. In the early universe, gravity won. Regions slightly denser than average collapsed into galaxies. But accelerating expansion makes this harder. Eventually, expansion will be so fast that no new large structures can form. The cosmic web of galaxies and clusters we see today is probably as big and complex as it will ever get. Existing structures held together by gravity will survive, Our local group of galaxies won't expand apart because gravity binds it tightly. The Milky Way, Andromeda, and a few dozen smaller galaxies will remain connected. But everything beyond that will recede faster and faster. Light from distant galaxies is already redshifted by expansion. As acceleration continues, the redshift increases. Eventually, light from galaxies beyond a certain distance will be redshifted to such long wavelengths that it becomes undetectable. These galaxies will effectively vanish from view, not because they've been destroyed, but because their light can no longer reach us. In about 100 billion years, most galaxies currently visible will have crossed beyond the cosmic event horizon. Only our local group will remain. Future observers would look out and see a much emptier universe. They'd have no way to discover the Big Bang or cosmic expansion, because the evidence, distant receding galaxies, would be gone. Some galaxies will remain visible, but only as frozen images. Light left those galaxies billions of years ago. The galaxies themselves have long since crossed the horizon. We're seeing their past, not their present. This creates a peculiar situation where the observable universe contains images of galaxies that no longer exist in observable reality. Cosmic acceleration also affects the ultimate fate of the universe. Without acceleration, the universe would either collapse or expand forever while cooling and diluting. With acceleration, expansion not only continues but speeds up. The universe heads toward a cold, empty, dark future. Heat death, maximum entropy. No more star formation. No more galaxies forming, just remnants expanding apart into infinite dark isolation. This future is trillions of years away, but acceleration guarantees it. Unless dark energy changes behavior, which it might, or some unknown physics intervenes. The discovery of cosmic acceleration was revolutionary. It revealed a new component of the universe, dark energy that dominates everything else. It changed our understanding of cosmology and the universe's fate, and it earned Saul Perlmutter, Brian Schmidt, and Adam Ries the 2011 Nobel Prize in Physics. The universe isn't slowing down, it's speeding up, and that changes everything about where we came from and where we're going. In 1917, Albert Einstein faced a problem. His brand new general relativity equations predicted that the universe should be either expanding or contracting. But everyone at the time believed the universe was static, eternal, and unchanging. Einstein trusted the prevailing wisdom over his own equations, so he modified them. He added a term called the cosmological constant, represented by the Greek letter lambda, La. This constant represented a repulsive force that could exactly balance gravity, keeping the universe static. The equations worked. The universe could be stable. Problem solved. Except the universe isn't static. In 1929, Edwin Hubble showed that distant galaxies are receding from us. The universe is expanding. Einstein's original equations were right. The modification was unnecessary. He reportedly called the cosmological constant his biggest blunder and removed it. For decades, the cosmological constant disappeared from cosmology. It was a historical footnote, a rare mistake by Einstein. The universe was expanding, slowing down due to gravity, heading toward either eternal expansion or eventual collapse. No cosmological constant needed. Then came 1998, the discovery that the universe's expansion is accelerating. Gravity alone couldn't explain it. Something was pushing space apart. The simplest explanation was a cosmological constant. Einstein's blunder wasn't a blunder. It was a real feature of the universe. He'd just used it for the wrong purpose. The cosmological constant represents vacuum energy. Even completely empty space, devoid of matter and radiation, has energy. This might sound strange. How can nothing have energy? But quantum mechanics says empty space isn't truly empty. Virtual particles constantly pop into and out of existence. These quantum fluctuations contribute energy to the vacuum. This vacuum energy has a peculiar property: negative pressure. In ordinary matter, pressure is positive. Compress gas in a container and it pushes back. But vacuum energy does the opposite. It has negative pressure, and in general relativity, negative pressure creates repulsive gravity. It pushes space apart. If the cosmological constant is real, it's been there all along, from the Big Bang to now. Its value is constant, the same everywhere and at all times, but its effects vary. In the early universe, when matter and radiation were dense, their gravity dominated. The cosmological constant was too weak to matter. Expansion decelerated as expected. But as the universe expanded, matter and radiation became dilute. Their density decreased. The cosmological constant didn't. Vacuum energy has the same density per unit volume regardless of expansion. Eventually, around 5 billion years ago, the cosmological constant's repulsive effect overtook matter's attractive gravity. Expansion started accelerating. Today, the cosmological constant, if that's what dark energy is, makes up about 68% of the universe's energy content. It dominates, and its dominance will only increase as matter continues diluting. This resurrection of the cosmological constant answers one mystery: why expansion is accelerating but creates another. Why is the cosmological constant so small? Quantum field theory predicts vacuum energy should exist. When you calculate its value, you sum contributions from quantum fluctuations of all fields at all energy scales. The result is enormous. About 10 circumflex, 120 times larger than the observed cosmological constant. This is the cosmological constant problem. A factor of 10 circumflex. 120 isn't a small discrepancy. It's the worst prediction in the history of physics. Off by 120 orders of magnitude. If the calculation were right, the cosmological constant would be so large that the universe would have exploded into expansion so violently that no structures, no galaxies, no stars, nothing could form. We wouldn't exist. Something is wrong. Either the calculation is missing, cancellations we don't understand, or there's new physics that suppresses vacuum energy, or we're fundamentally misunderstanding how quantum mechanics and gravity interact. Some physicists invoke the anthropic principle. Maybe the cosmological constant varies across a multiverse of universes. Most universes have large values and don't form galaxies or life. We exist in one, with a tiny value because only those universes produce observers. Selection bias. Not everyone finds this satisfying. Others propose that vacuum energy gravitates differently than we think. Maybe quantum contributions to vacuum energy don't curve spacetime the way ordinary energy does. This would require new physics, beyond general relativity and quantum field theory. Supersymmetry, if it exists and is unbroken, would make certain cancellations between particles and their superpartners, potentially reducing vacuum energy. But supersymmetry appears to be broken if it exists at all, and we don't understand the breaking mechanism well enough to calculate the resulting vacuum energy. The cosmological constant problem is unresolved. We observe a small but non-zero value. Theory predicts a huge value. The discrepancy is staggering. Explaining it might require a revolution in our understanding of quantum mechanics, gravity, or both. Einstein's biggest blunder wasn't a blunder. The cosmological constant is real. But why it has the value it does remains one of the deepest mysteries in physics. Solving it will likely require insights we haven't discovered yet, and the answer might reshape our understanding of reality itself. Physics prides itself on precision. Quantum electrodynamics predicts the electron's magnetic moment to 12 decimal places. Matching observations. General relativity predicts gravitational time dilation to extraordinary accuracy. GPS depends on it. These are triumphs. Physics works. Then there's the cosmological constant, the worst prediction in physics. Off by 120 orders of magnitude. Not 10%, not a factor of 2, not even a factor of 1,000,000. A factor of 10 circumflex. 120. A 1 followed by 120 zeros. Here's the problem. According to quantum field theory, empty space isn't empty. It's filled with fields. The electromagnetic field, quark fields, electron fields, dozens of fields corresponding to all known particles. And these fields fluctuate. Even in their lowest energy state, the vacuum, they're jittering due to quantum uncertainty. These fluctuations have energy. Each little quantum jitter contributes a tiny amount. Sum over all possible fluctuations of all fields, and you get the vacuum energy. This energy should gravitate. It should curve spacetime. It should act like a cosmological constant. Calculate it, and you get infinity. That's because you're summing over all possible wavelengths of fluctuations, including arbitrarily short wavelengths with arbitrarily high energy. Obviously, infinity is wrong. The universe exists, so vacuum energy isn't infinite. Physicists cut off the calculation at some maximum energy. A reasonable cutoff is the Planck energy, about 10 circumflex 19 GeV. This is where quantum gravity effects become important, and our theories break down. Don't trust calculations beyond this scale. With this cutoff, the vacuum energy comes out to about 10 circumflex, 113 joules per cubic meter. Convert that to the units cosmologists use, and it corresponds to a cosmological constant about 10 circumflex 120 times larger than observed. The universe should be expanding so violently that atoms couldn't hold together, galaxies couldn't form, we shouldn't exist. But we do exist. So the actual vacuum energy is smaller, much, much smaller. Observations constrain it to about 10 circumflex, 9 joules per cubic meter. That's the value consistent with the observed acceleration of cosmic expansion. How do you get from 10 circumflex 113 to 10 circumflex 9? You need a cancellation, something that almost perfectly cancels the huge quantum fluctuations, leaving only a tiny residual value. And that cancellation has to work to 120 decimal places. This seems absurdly fine-tuned. Imagine balancing a pencil on its point. Hard, but possible. Now imagine balancing it to within a nanometer of perfect verticality. Much harder. Now imagine balancing it to within a trillionth of a nanometer. That's the level of fine-tuning required for the cosmological constant. Why would nature choose such an improbably tiny value? There's no known mechanism. Symmetries can sometimes produce exact cancellations. If the universe had a perfect symmetry, positive and negative contributions to vacuum energy might exactly cancel, giving zero. But we know the cosmological constant isn't zero. It's small, but positive. What symmetry gives a tiny value instead of zero or huge? Supersymmetry was hoped to help. This hypothetical symmetry relates bosons and fermions. In a perfectly supersymmetric universe, their contributions to vacuum energy would exactly cancel. Zero cosmological constant. But supersymmetry, if it exists, is broken in our universe. Bosons and fermions don't have matching masses. The cancellation is imperfect. How imperfect? We don't know because we don't understand how supersymmetry is broken. Another approach invokes the anthropic principle and the multiverse. Maybe the cosmological constant varies randomly across different universes. Most universes have large values. Only a tiny fraction have small enough values for galaxies and life to form. We exist in one of those rare universes because we couldn't exist anywhere else. Observer selection bias. This explanation bothers many physicists. It doesn't predict a specific value. It just says the value we observe is unsurprising given that we exist. It's not falsifiable in the traditional sense, and it requires a multiverse, which might be real, but which we can't observe directly. Some suggest quantum gravity will resolve the problem. Maybe at the Planck scale, space-time becomes discrete or non-geometric in ways that eliminate the divergent contributions to vacuum energy. String theory, loop quantum gravity, or some other quantum gravity theory might naturally produce a small cosmological constant, but we don't have a complete quantum gravity theory, so we can't calculate this. Others propose that vacuum energy doesn't gravitate the way we think. Maybe there's a screening mechanism. Perhaps general relativity needs modification at cosmological scales, introducing new fields or interactions that suppress vacuum energy's gravitational effects. These are speculative and lack compelling theoretical motivation. The cosmological constant problem connects quantum mechanics and gravity in a way we don't understand. The calculation uses quantum field theory in flat spacetime. It ignores gravity and back reaction. Maybe that's the problem. Maybe you can't calculate vacuum energy without fully accounting for spacetime curvature and quantum gravity. But we don't know how to do that calculation. This is humbling. We can calculate exquisitely precise predictions for atomic physics. We detected gravitational waves from black holes colliding 1 billion light-years away, but we can't explain the value of the cosmological constant. Off by 120 orders of magnitude. The worst prediction in physics, and we have no idea how to fix it. Solving this problem will require new insights, possibly new physics, probably a deeper understanding of how quantum mechanics and gravity fit together. Until then, the cosmological constant problem stands as a monument to our ignorance. A reminder that despite our successes, fundamental aspects of reality remain profoundly mysterious.